Please subscribe to support the channel. Will humanity ever leave our solar system? That question sits at the crossroads of science, philosophy, and imagination. It's not just a technical problem, it's a profound riddle about our future, our survival, and our place in the universe. When you think about it, everything we know, everything we've ever done as a species, every human who has ever lived, has been under the protective bubble of our sun's influence. Our triumphs, our failures, our civilizations, and even our dreams have all unfolded within this small neighborhood of the cosmos. So, when we ask the question, will humanity ever leave the solar system? We're asking something much bigger than just a scientific curiosity. We're really asking, can we transcend our birthplace? Can we become a species that roams the stars, instead of being forever confined to one tiny corner of space? This opening question carries with it a sense of mystery and scale that no other human endeavor quite matches. We're not talking about crossing an ocean, flying across continents, or even landing on another planet within our system. We're talking about breaking free from the cradle that has held us for billions of years, and venturing into the vast, cold, almost incomprehensibly large space between the stars. It's the ultimate leap of exploration, the boldest step we could ever take as a species. And yet, when we pose that question, it also challenges us. Because if the answer is yes, then we are forced to face just how daunting that journey will be. And if the answer is no, then we must also face the reality that we may forever be bound to this one little solar system. Perhaps vulnerable, perhaps temporary. The very act of asking, will we ever leave the solar system, forces us to think about ourselves in a cosmic context. It makes us confront the scale of the universe, the limits of our technology, and the resilience of human ambition. It sparks both hope and humility. Hope, because the stars are there, beckoning, waiting to be reached. Humility, because the distances involved are so immense that even our fastest machines crawl at the pace of a cosmic snail compared to what would be required. So as we begin this exploration of the question, keep in mind that this isn't just about physics or engineering, it's about identity. It's about whether humanity's destiny lies among the stars, or whether we will remain forever tied to the light of our sun, gazing outward but never stepping beyond. Why does it matter whether humanity ever leaves the solar system? The answer lies in what that journey represents, not just for science, but for the entire trajectory of our species. For most of human history, our world was limited by the horizon. We were bound to small regions of Earth, never fully aware of what lay beyond. But as time passed, curiosity and necessity drove us outward. People crossed deserts, climbed mountains, sailed across oceans, and eventually flew into the skies. Each leap expanded our perspective and transformed us. Yet no leap in history compares to the idea of leaving the solar system. That's not just stepping into new land, it's stepping into a new epoch of existence. At this moment in history, we are still a planetary species. Everything about our survival depends on Earth. Our air, our food, our water, our climate, it's all tied to this fragile planet. Even though we've sent probes across the solar system, even though astronauts have walked on the moon, even though space stations orbit above us, humanity itself is still chained to one planet, within one solar system. If anything happened to Earth, whether by natural disaster, asteroid impact, runaway climate catastrophe, or something entirely unpredictable, our entire species could be wiped out in a geological blink of an eye. To leave the solar system would mean we are no longer confined to a single place. It would be the transition from a species vulnerable to extinction to one with a chance of survival on cosmic timescales. There's another layer to why it matters: imagination. The human spirit thrives on exploration. Every frontier we've crossed has expanded not only our geography, but also our culture, our science, and our understanding of ourselves. Think about the night sky for a moment. For thousands of years, our ancestors looked up at the stars and wondered what they were, what worlds might orbit them, whether beings might live there. To finally cross into the interstellar realm would be to fulfill one of the oldest dreams of humanity, the dream of touching the stars, not just with our eyes, but with our presence. Becoming an interstellar species would also change how we see ourselves. Right now, nations argue, cultures clash, and humanity feels fragmented. But on the scale of the cosmos, all of us are one small family on a tiny blue planet circling an ordinary star. To step beyond the solar system would emphasize that truth. It would remind us that humanity is not defined by borders, but by the shared destiny of our species. In a sense, leaving the solar system isn't just about reaching new places. It's about maturing into something larger, something that sees survival, cooperation, and exploration as intertwined. Technologically, it matters because the attempt itself would drive progress in ways we can hardly imagine. To prepare for such a journey, we'd have to solve some of the hardest problems in physics, biology, engineering, and even sociology. How do you build machines that last centuries? How do you keep humans alive in deep space for generations? How do you generate energy in the void between stars? Each of these challenges, if overcome, would produce breakthroughs that ripple back to Earth, advancing medicine, clean energy, artificial intelligence, and sustainability. In that sense, the dream of leaving the solar system isn't only about what lies out there, it's also about transforming life back here. It also matters because of what lies beyond. Astronomers have discovered thousands of planets orbiting other stars, and the number is growing rapidly. Many of them are Earth-sized, some in the so-called habitable zone where liquid water could exist. That raises the tantalizing possibility that some of these worlds may harbor life, perhaps even intelligent life. The only way to find out for certain is to go. Telescopes can give us clues, but nothing compares to the direct exploration of distant systems. If we remain confined to our solar system, we remain confined in our knowledge. But if we leave, we gain access to a universe of possibilities. On a philosophical level, leaving the solar system would mark the moment humanity stops being local and becomes cosmic. Imagine future historians looking back thousands of years from now. They might divide human history into two great eras, the age of earthbound humanity and the age of interstellar humanity. The moment we cross the solar system's boundary will be remembered as the dividing line. That's why it matters, because it's the kind of transition that defines not just a century, not just a millennium, but the very destiny of our species. And perhaps the most profound reason of all is this: time is long, and stars do not last forever. Our sun will shine for billions more years, but eventually, it too will die. If humanity is still confined to the solar system when that happens, then we perish with it. The only way to ensure that our story continues is to reach other stars. To remain here is to accept eventual extinction. To leave is to embrace survival on a scale as vast as the cosmos itself. So when we ask whether humanity will ever leave the solar system, we are not asking a trivial question. We are asking about survival, imagination, unity, discovery, progress, and destiny. It matters because it is the ultimate test of whether we are a fleeting species or one that endures. It matters because it will decide whether our story ends on one world or spreads across the galaxy. It matters because to remain is to be temporary, but to leave is to be eternal. When people talk about leaving the solar system, it sounds simple at first. You might imagine a spacecraft flying past Neptune or maybe passing Pluto, and then, just like that, it's out of the solar system. But in reality, the definition is much more complicated, and it's important to understand what that phrase truly means. Our solar system isn't just a collection of planets orbiting the sun. It's a vast bubble of influence, shaped not only by gravity but also by the sun's radiation, magnetic fields, and the stream of charged particles it constantly throws out into space. That bubble is what we call the heliosphere, and it's the boundary of this heliosphere, known as the heliopause, that astronomers typically use to define the outer edge of the solar system. The sun is not just a ball of light sitting in space. It's an active, dynamic star that constantly emits a flow of charged particles known as the solar wind. These particles race outward in all directions at speeds of hundreds of kilometers per second. As they rush outward, they create an invisible bubble around our entire planetary system. Inside this bubble, the solar wind dominates, pushing against the thin gas and dust that exists between the stars, what we call the interstellar medium. This bubble is enormous. To put it in perspective, Earth is about 150 million kilometers from the Sun, but the heliosphere stretches out more than 100 times that distance in every direction. That means the boundary of the solar system, in terms of the Sun's influence, is not just beyond Pluto, it's many times farther out. At some point, the solar wind loses its strength. It slows down, it gets compressed, and eventually it collides with the interstellar medium pushing back from outside. That's where we find the heliopause, the point where the sun's influence ends and true interstellar space begins. This is not a sharp edge like a wall, it's more like a shifting frontier. The position of the heliopause can change depending on solar activity and the density of the interstellar medium outside. But on average, it sits at roughly 120 to 150 astronomical units, AU, from the Sun. For comparison, Neptune orbits at about $30 and Pluto around $39. So leaving the solar system is not just about passing the last planet. It's about going 3 or 4 times farther out than Pluto before crossing into a realm where the Sun's protective bubble no longer shields us. To make this clearer, imagine standing in a windy field. As long as you're inside the reach of the wind, you feel its push against your skin. Walk far enough away, and eventually, you step into an area where the wind no longer touches you. That's essentially what happens at the heliopause. Inside it, you're in the Sun's space. Beyond it, you're in the galaxy's space. It's the true frontier between our local star system and the broader Milky Way. This definition is crucial, because without it, we risk misunderstanding what leaving the solar system really means. For example, Pluto, though distant, is still firmly inside the Sun's heliosphere. Even a spacecraft traveling far beyond Pluto, like New Horizons, remains inside the solar system until it crosses the heliopause. It's only when we go beyond that invisible line that we can say we've entered interstellar space. It's also worth noting that gravity complicates this definition even further. The Sun's gravity actually extends much farther out than the heliosphere, pulling comets and icy bodies in the Oort cloud into its domain. The Oort cloud is a theoretical shell of icy debris thought to surround the solar system, extending out perhaps 50,000 to 100,000 Australian dollars from the Sun. That's about halfway to the nearest stars. In that sense, the Sun's gravitational influence stretches almost unimaginably far into space. So technically, if you use gravity as your marker, we never truly leave the solar system until we cross into another star's gravitational territory. But for practical purposes, scientists usually define the heliopause as the boundary, because it represents the limit of the Sun's immediate power over the environment of space. Crossing the heliopause is not just symbolic, it's scientifically significant, too. Inside the heliosphere, we're protected by the solar wind, which acts like a shield against a large portion of cosmic radiation. Outside the heliosphere, spacecraft are exposed directly to the harsher radiation of interstellar space. This makes the heliopause an important physical transition zone, not just a conceptual one. The data we've received from the Voyager spacecraft after they crossed this boundary has already transformed our understanding of how stars interact with their galactic environment. So, when we talk about humanity one day leaving the solar system, we mean more than just drifting past the planets. We mean pushing beyond the heliosphere, past the heliopause, and into the wild expanse of the galaxy itself. It's a threshold that separates the comfort of our Sun's domain from the infinite frontier beyond. And once we cross it with human presence, not just robotic probes, it will be one of the most historic milestones in the history of our species, because it will mean that for the first time, humanity has stepped outside the cradle of its star and entered the universe on its own terms. In the story of humanity's attempt to reach beyond the solar system, the names Voyager 1 and Voyager 2 shine brighter than almost any others. These twin spacecraft, launched in 1977, were not originally intended to become interstellar pioneers. They were built to explore the outer planets, to take advantage of a rare planetary alignment that happens only once every 176 years. This alignment allowed a single spacecraft to slingshot from one giant planet to the next using gravity assists, saving fuel and drastically reducing travel time. The Voyagers were sent to study Jupiter and Saturn, and in Voyager 2's case, Uranus and Neptune as well. But because of their speed, their trajectory, and their robust engineering, both probes eventually pushed farther than any spacecraft before, becoming the first human-made objects to cross into interstellar space. Their journeys mark a kind of first step into the broader galaxy. Voyager 1 launched on September 5, 1977, shortly after its sibling Voyager 2, which lifted off on August 20th of the same year. Voyager 2's name might sound like it came later, but it was actually launched earlier because of orbital timing. Both carried instruments to capture images, measure magnetic fields, detect cosmic rays, and analyze the composition of planetary atmospheres. The early parts of their missions were dazzling successes. Voyager 1 revealed the turbulent atmosphere of Jupiter, captured stunning images of its great red spot, and gave us our first close looks at volcanic eruptions on Io, the first active volcanoes ever seen beyond Earth. Voyager 2, continuing onward, became the only spacecraft ever to fly past Uranus and Neptune, showing us their mysterious bluish atmospheres, their dark rings, and moons we never knew existed. But after their planetary tours ended, something remarkable happened. Instead of shutting down, both spacecraft continued on escape trajectories, coasting outward from the Sun at incredible speeds. Their paths carried them toward the very edge of the Sun's influence, the heliopause. And so, by accident of design and foresight, the Voyagers became ambassadors to the stars. Voyager 1, traveling faster, was the first to reach interstellar space. On August 25, 2012, at a distance of about 121 astronomical units. That's roughly 18 billion kilometers from Earth, it crossed the heliopause. This was humanity's first physical step into the space between the stars. Voyager 2 followed years later, crossing into interstellar space in November 2018 at about 119 astronomical units. These were moments of quiet history, not like the dramatic moon landing with astronauts waving flags, but still deeply profound. Humanity had finally extended its touch beyond the Sun's protective bubble. What makes this achievement extraordinary is how long the Voyagers have lasted. Built with 1970s technology, they are still communicating with Earth nearly 5 decades later. Their power comes from radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium-238 into electricity. These power supplies are slowly dwindling, and NASA has had to turn off one instrument after another to conserve energy. Yet, even today, they continue to send faint signals back across the void, picked up by the giant dishes of the Deep Space Network. Each signal takes over 22 hours to reach Earth, traveling at the speed of light. When you consider that these spacecraft are still functioning, still whispering data to us after so long, it's almost poetic. Tiny messengers of humanity drifting in the darkness, still loyal to their mission decades after launch. The significance of the Voyager's crossing into interstellar space is immense. For the first time, we were able to directly sample the conditions beyond the heliosphere. Inside the solar system, the solar wind dominates, but outside, the environment changes drastically. Voyager's instruments detected higher levels of galactic cosmic rays, different plasma densities, and shifts in magnetic field orientation. These discoveries confirm that the heliopause is a real, measurable boundary, an invisible frontier between the influence of our Sun and the rest of the galaxy. Before the Voyagers, this was only theory. After them, it became fact. And then there is the cultural side of their journey. Both Voyagers carry something unique, the Golden Record. This was a brainchild of Carl Sagan and a team of scientists and artists who wanted to place a message from humanity aboard these spacecraft. The Golden Record is a copper phonograph disc, gold-plated for longevity, carrying sounds and images chosen to represent the diversity of life and culture on Earth. There are greetings in 55 languages, sounds of nature like thunder, wind, and whale songs, music ranging from Bach to Chuck Berry, and images showing landscapes, human anatomy, scientific diagrams, and moments of life across our planet. The record also includes instructions on how to play it and a map pointing to our location in the galaxy. The idea was that, perhaps millions of years from now, if an alien civilization were ever to encounter one of these craft, they might learn something about the strange beings who sent them. The Golden Record turns the Voyagers from mere machines into ambassadors of Earth's story. In practical terms, though, we must remember how slow they are moving relative to the vastness of space. Voyager 1 is traveling at about 17 kilometers per second relative to the Sun. That might sound incredibly fast, faster than any bullet, but in cosmic terms, it's glacial. At that speed, it would take over 70,000 years for Voyager 1 to reach the nearest star system, Proxima Centauri, which is just 4.2 light-years away. So, while the Voyagers are technically on their way to the stars, they will never reach them in any meaningful human time frame. By the time they pass even within a few light-years of another star, Earth may look completely different, our civilizations long gone, perhaps even our species transformed or extinct. Yet, their symbolic role is profound. Voyager 1 and 2 are proof that we can build machines to leave the solar system, even if only as slow drifters. They show that humanity has already taken its first, tentative step into the wider galaxy. They are markers of possibility, reminders that the edge is not unreachable. They also demonstrate the power of foresight. In the 1970s, scientists and engineers built something so durable, so resilient, that it outlasted expectations by decades and became an interstellar pioneer. That tells us something important about ourselves. Given vision and determination, humanity can create machines, and perhaps one day, ships carrying people, that push past the boundaries of the known. And so, as the Voyagers continue their lonely flight, they carry not just data, not just the golden records, but also a sense of destiny. They are our eyes and ears in a realm no human has ever touched. They are the farthest expressions of our curiosity, stretching out into the cosmos. Every signal they send back is a reminder that we are capable of reaching beyond our world, that the dream of leaving the solar system is not science fiction but a real, ongoing journey. They may be tiny compared to the universe, but they are immense in what they represent, the beginning of humanity's path into interstellar space. When we say that Voyager 1 has entered interstellar space, it sounds almost like a triumph that puts us halfway to the stars. But in truth, it reveals just how staggeringly vast the universe is, and how painfully slow our current technology really is when compared to the distances involved. Voyager 1 is the farthest human-made object from Earth, farther than anything else we've ever launched. Right now, it is over 23 billion kilometers away, which is about 156 astronomical units from the Sun. That distance alone is difficult to comprehend. Light, which travels at 300,000 kilometers per second, takes about 21.5 hours to reach Voyager 1 from Earth. That means every time NASA sends a signal to the spacecraft, it's almost a full day before the spacecraft hears it, and then another day before its reply reaches us. So, yes, it's unimaginably far by human standards. But compared to the nearest star, it's barely out of the driveway. To put things into perspective, let's talk about Proxima Centauri, the closest star to our Sun. It's part of the Alpha Centauri system and lies about 4.24 light-years away. A light-year is the distance light travels in a year, and since light is the fastest thing in the universe, this is an almost unimaginably huge distance. 1 light-year equals about 9.46 trillion kilometers. Multiply that by 4.24, and you get around 40 trillion kilometers. Compared to that, Voyager's 23 billion kilometers is like walking a few steps on the beach when the ocean stretches endlessly beyond the horizon. Voyager hasn't even gone 1,000th of the distance to the nearest star. In fact, if you shrank the Milky Way galaxy down to the size of the continental United States, Voyager would not have left your front yard yet. Now, let's consider its speed. Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun. That's blisteringly fast compared to anything we experience in everyday life. At that speed, you could circle Earth in about 23 minutes. It's also about 60,000 kilometers per hour. But when you compare it to the scale of interstellar travel, it's like crawling. At this pace, as mentioned before, Voyager 1 would take around 70,000 years to reach Proxima Centauri. Think about that number. 70,000 years. That's longer than all of recorded human history. 70,000 years ago, Homo sapiens were still sharing the planet with Neanderthals. Our ancestors were chipping stone tools, making cave art, and living in small tribes. If Voyager were a ship carrying humans, entire civilizations would rise and fall, languages would evolve, species might change, and continents might reshape themselves before the ship even arrived at the nearest star. This reality tells us something sobering. With current propulsion methods, interstellar travel is not just impractical, it is almost impossible on human timescales. Voyager's journey makes this painfully clear. Even though it's a marvel of engineering, even though it has crossed into interstellar space, it is still trapped in a kind of cosmic crawl. It shows us that crossing into interstellar space and reaching another star are two very different things. One is a symbolic milestone, an accomplishment that proves we can build machines to leave the Sun's bubble. The other requires technology that surpasses anything we currently have. It also raises an interesting point about perspective. From our human viewpoint, Voyager's position is staggering. It has gone farther than any of us could ever dream of traveling in a lifetime. But from the galaxy's perspective, Voyager hasn't gone anywhere at all. The stars don't notice it. It hasn't even passed the outer regions of the Oort cloud, the distant shell of icy objects that surrounds our solar system. Some scientists estimate that it could take Voyager tens of thousands of years just to exit the Oort cloud entirely. So while we celebrate its entry into interstellar space, we also have to accept the humbling truth: we've barely dipped a toe into the cosmic ocean. And yet, that's exactly why Voyager matters so much. It doesn't just represent our first step outward, it represents a stark demonstration of the scale of the challenge ahead of us. By looking at Voyager's progress and comparing it to the distances involved, we begin to grasp the enormity of interstellar travel. It's one thing to dream about visiting another star system, another Earth-like world orbiting in a distant sun's glow. It's another thing entirely to calculate the travel time using our fastest spacecraft and realize that it stretches beyond the span of human civilization itself. But here's the paradox: Voyager's slowness doesn't make its journey meaningless. In fact, it makes it more profound. Because even though it is so small, so slow, and so fragile, it has still left the only home we've ever known. It shows us that the step into the interstellar realm isn't a matter of sheer speed. It's a matter of persistence, engineering, and vision. Voyager is, in a sense, humanity's seed drifting into the cosmos. It may never reach another star, but it proves that we can break free from the sun's protective cradle. For scientists, this perspective is crucial. Voyager has already given us real data from interstellar space, things we could never have learned without crossing the heliopause. For dreamers, it is a reminder that the stars are still unimaginably far, but not unreachable. The lesson is clear: to truly reach another star within a human lifetime, we will need new physics, new engineering, and new approaches. Voyager shows us the scale of the task, and in doing so, it challenges us to rise to it. In the end, what Voyager's distance and speed really mean is this: humanity has already taken its first step into the cosmos, but the path ahead is thousands of times longer than the step we've taken. It's like placing your foot across the threshold of your door and realizing the road you must walk stretches across the entire planet. The enormity of that road doesn't make the first step less important, it makes it all the more historic. After the Voyagers, one of the most celebrated spacecraft to push into the outer reaches of our solar system is New Horizons, a mission that captured the world's imagination in 2015 when it delivered the first close-up images of Pluto. Unlike Voyager 1 and 2, which were conceived as grand tour missions to multiple gas giants, New Horizons had a singular, daring purpose: to finally visit the mysterious world that had been little more than a faint, blurry smudge in telescopes for nearly a century. Launched on January 19, 2006, New Horizons was one of the fastest spacecraft ever sent from Earth. It left our planet at nearly 58,000 kilometers per hour, breaking records for the highest launch speed of a human-made object at that time. Its trajectory was carefully planned, using a gravity assist from Jupiter in 2007 to boost its velocity even further. After nearly a decade of travel through the cold, empty regions beyond Neptune, New Horizons finally arrived at Pluto in July 2015. The images it sent back were breathtaking. For decades, Pluto had been depicted as a frozen, featureless ice ball. But New Horizons revealed an active, surprising world. It showed us vast plains of frozen nitrogen, mountains made of water ice, hazy blue skies, and even evidence of geological activity that suggested Pluto is not a dead world but a dynamic one. The famous heart-shaped region, informally named Tombor Regio after Pluto's discoverer Clyde Tombaugh, captured the hearts of people around the world. In a sense, New Horizons reminded humanity that even the most distant corners of our solar system are full of wonders waiting to be discovered. But Pluto wasn't the end of the road. After its flyby, NASA extended New Horizons' mission into what's called a Kuiper Belt Extended Mission, KEM. The Kuiper Belt is a vast region beyond Neptune, populated by icy remnants from the formation of the solar system, essentially a cosmic fossil field. In 2019, New Horizons made a close flyby of a small Kuiper Belt object, KBO, officially named Arrokoth, formerly nicknamed Ultima Thule. The images showed a contact binary, a peanut-shaped body formed from two smaller objects that had gently merged billions of years ago. This was the most distant object ever visited by a spacecraft, providing direct evidence of how planetary building blocks formed in the early solar system. Today, New Horizons continues to travel outward, although at a much slower pace than Voyager 1 or Voyager 2. It is currently moving at about 14 kilometers per second relative to the Sun, still incredibly fast by human standards, but slower than the Voyagers. Unlike the Voyagers, New Horizons is not on a trajectory to escape the solar system quickly. It will eventually reach interstellar space, but that moment lies far in the future. Some estimates suggest it could cross the heliopause in about 100 years or so, assuming it continues functioning long enough. Unfortunately, its power source will run out decades before that. Like the Voyagers, New Horizons is powered by a plutonium RTG, and as the fuel decays, the spacecraft will eventually fall silent. Despite this, its legacy is already secure. New Horizons gave humanity its first intimate look at Pluto and pushed deeper into the Kuiper belt than we had ever gone. It also demonstrated that missions to the distant outer solar system are possible with clever engineering and patient planning. Perhaps most importantly, it built on the spirit of the Voyagers, extending humanity's reach outward, further from the Sun, and into regions that had never before been explored. When we talk about leaving the solar system, New Horizons doesn't carry the same symbolic weight as Voyager 1 or 2, because it hasn't yet crossed into interstellar space. But it adds a crucial piece to the story. It shows that we are not just flinging spacecraft outward randomly, we are charting the solar system step by step, target by target, world by world. Before we can dream of leaving for other stars, we must first understand the full extent of our own backyard. New Horizons is part of that process. It is worth noting that, unlike Voyager, New Horizons doesn't carry a golden record or any symbolic message to future civilizations. Its mission was focused on science, not on being an ambassador. Yet, in a way, it still serves that role. The images of Pluto and Arrokoth are now woven into human culture, a reminder of what's possible when we aim our technology outward and dare to reach faraway places. Each probe, like New Horizons, is a stepping stone, building knowledge and inspiring the next leap forward. So while Voyager may be humanity's first emissary to the stars, New Horizons represents something equally important: the continuation of exploration into the uncharted regions of our own system. It's the link between the planetary age of exploration and the interstellar ambitions that lie ahead. One day, when humanity finally does send starships into the galaxy, missions like New Horizons will be remembered as the scouts that first taught us what it means to travel far into the cold, dark outer reaches of the solar system and still uncover beauty, mystery, and discovery. If you really want to feel the weight of the cosmos, start with a clean number. Proxima Centauri, the nearest star to our Sun, sits a little over 4.2 light-years away. A light-year isn't time, it's distance. The span light covers in a year while racing at the ultimate speed limit of the universe. 1 light-year is roughly 9.46 trillion kilometers. Multiply that by a little over 4.2, and you're staring at a gulf of about 40 trillion kilometers. 40 trillion kilometers. You could line up every highway on Earth end to end, stack every airline route, lace the planet with racetracks from pole to pole, and the result would still be a rounding error compared to that distance. Light itself, nature's fastest courier, needs more than 4 years to make the trip. A radio message beamed today wouldn't caress Proxima's planets until late in the decade, and any reply wouldn't return until the early 2030s. That's how far near is in astronomy. Numbers this big are slippery, so let's tame them with scale. Astronomers often measure solar system distances in astronomical units, AU, where $1 is the average Earth-Sun distance, about 150 million kilometers. Proxima Centauri sits around 268,000 Australian dollars away. Now imagine shrinking the solar system so that $1 equals a single centimeter, about the width of your fingernail. On that map, Earth orbits the Sun just 1 centimeter out. Neptune is comfortably parked at about 30 centimeters. The heliopause, the edge of the Sun's protective bubble, hovers roughly 1 to 1.5 meters away. Where's Proxima? Keep walking. Past the doorway. Down the street. 2.7 kilometers from your model Sunday. In the classroom of the galaxy, the nearest desk is still across town. That distance turns our proudest feats of engineering into acts of exquisite patience. Voyager 1, the farthest human artifact, now cruises beyond the heliopause at roughly 17 kilometers per second. That's fast enough to lap Earth in about 23 minutes. It's also fast enough to make a rocket scientist smile and a star traveler sigh. At 17 kilometers per second, the 40 trillion kilometer slog to Proxima burns roughly 75,000 years. Pause on that timescale. When 75,000 years roll by, languages have time to be born, branch, and go extinct. Coastlines redraw themselves, ice ages advance and retreat, entire civilizations arc from myth to memory. If Voyager had launched when the first cave paintings were fresh, it would just now be arriving. New Horizons, the Pluto explorer, moves a little slower, about 14 kilometers per second, and would need on the order of 90,000 years. Even the Parker Solar Probe, which dives so close to the Sun that it becomes the fastest thing humans have ever built relative to the Sun, has flirted with heliocentric speeds approaching ~190 km/s during its swoops. Lock that speed in a straight interstellar line and the Proxima trip still stretches to something like 6,700 years. That's the difference between fast and astronomically far. Everyday transportation drives the point home with a kind of grim humor. A jetliner. At 900 km/h, you're looking at around 5 million years of flight time. A car at highway speed? Tens of millions of years of humming tires and rest stops that never end. The cosmos laughs gently at our engines and then invites us to dream bigger. It's tempting to think, all right, but what if we really floor it? What about a tenth the speed of light? At 0.1 c, 30,000 km per second, the trip to Proxima would last about 40+ years, which is finally a human lifetime number. At 0.2 c, like the audacious laser sail concepts that have been proposed, you're flirting with a 20-something year cruise, not counting the headaches of slowing down at the destination. The catch is that leaping from tens of kilometers per second to tens of thousands isn't incremental, it's revolutionary. That gulf is where the frontier of propulsion lives: nuclear pulse schemes, fusion drives, beam-push sails, even exotic spacetime engineering. Until we cross that technological canyon, Proxima remains not just far, but functionally unreachable for crude craft. The human mind likes edges and borders, so we often blur the difference between outside the solar system and near another star. Voyager 1 crossed the heliopause. Yes, it shook the Sun's hand and stepped into the galaxy's breeze. But in terms of the grand map, it has only changed neighborhoods, not cities. The hypothetical Oort cloud, a vast spherical reservoir of icy bodies bound by the Sun's distant gravity, likely extends out to tens of thousands of AU, maybe even halfway to Proxima. Voyager may sail for tens of millennia before it escapes that ghostly shell entirely. The nearest star is close enough to neighbor our sky, yet far enough to redefine patience. Perspective also sharpens when we translate those 40 trillion kilometers into the currency of signals and stories. If you sent a hello today, Proxima's planets wouldn't hear you until more than 4 years from now. If someone over there, on a world we like to call Proxima b, answered immediately, their high back would rinse Earth's radio telescopes in the late 2030s. Any conversation becomes correspondence by bottle and tide, each reply bridging presidential terms, careers, even entire phases of life. The delay itself is a teacher. The universe is vast, and communication beyond our sun is, by default, a lesson in patience and planning. This is where the beauty and the bruise live together. On the one hand, 40 trillion kilometers is a dare. It tells us that the next era of exploration demands new tools, new physics, and a new relationship with time. On the other hand, the number is strangely inspiring. It is big enough to clarify our ambition. It forces precision, grit, and humility. It says, if you want the stars, you must build machines that sip power for centuries, or push payloads with beams of light, or harvest fusion in a bottle without losing the bottle. It says, you can go, but you must become different to do it. It's also instructive to zoom back in and compare scales we think we already understand. The Earth-Moon distance is about 1.3 light seconds. You could text the Moon and get a reply in under 3 seconds. The Sun is 8 light minutes away. A message to a Mars-bound rover can stretch to more than 20 minutes of one-way silence when the planets are misaligned. Proxima shrugs at minutes and stacks years. That hierarchy of light time is the skeleton key to our future. Near-Earth space is conversational, the inner solar system is deliberative, the outer solar system is monastic, and the interstellar medium is generational. To reach Proxima with people, you either go very, very fast, or you go very, very patient. Analogies can help, but they also reveal our bias toward smallness. If the Sun were a grain of sand on a beach, Earth would be a speck hugging its side, Neptune a speck a few handspans out, the heliopause may be a couple of long strides, and Proxima would be another grain downshore past cliff and cove, out of sight around the headland. We imagine space as an ocean because oceans are the largest thing our ancestors could cross. But the sea between stars is different. It isn't just big, it's structured by physics that punish mass and reward ingenuity. Sailing it will require us to master momentum like bankers master interest, to harvest energy like farmers read seasons, and to shield life as carefully as we shield hope. All of which leads to a simple, sobering, motivating truth. Proxima Centauri is near by the universe's standards and impossibly far by ours, unless we change what ours means. The distance is a mirror. It reflects our present limits and our future possibilities. It tells us we've done something incredible already, flinging tiny emissaries into interstellar space, and that we've only begun to learn how to stretch a human story across cosmic distances. It invites us to design machines that last longer than empires, to think in centuries without surrendering the urgency of now, and to treat each improvement in propulsion not as a curiosity but as a step on a staircase with a star at the landing. So yes, Proxima Centauri is just over 4 light-years away, 40 trillion kilometers, 75,000 Voyager years, 90,000 New Horizons years, 6 to 7 Centra Parker probe swoops if you could somehow harness that speed in a straight line and keep it. But don't let the arithmetic bruise you. Let it calibrate you. The distance is not a wall, it's a ruler. And rulers aren't there to stop you, they're there to help you measure the work ahead. If you take the nearest star problem and run it through the cold arithmetic of Voyager-class speeds, the romance of the night sky turns into a timeline so long it swallows civilizations. Start with the basic numbers. Proxima Centauri sits about 4.2 light-years away. A light-year is a distance, not a time. It's how far light travels in 1 year at roughly 300,000 kilometers per second. 1 light-year comes out to about 9.46 trillion kilometers. Multiply that by 4.2 and you land on an interstellar gulf on the order of 40 trillion kilometers. Written with all the zeros, that's approximately 40 trillion kilometers. Now put Voyager 1 into the picture. After decades of flight, it coasts at roughly 17 kilometers per second relative to the Sun. That speed comes from gravity-assist slingshots and a lot of patience, not from burning fuel continuously. It's fast for a spacecraft, glacial for a starbound traveler. To translate distance into time, divide the distance by the speed and then convert seconds to years. Let's do it cleanly so the scale sinks in. Take a round figure for the distance, 4.0 times 10 to the power of 13 kilometer. 40 trillion kilometers is a reasonable, conservative stand-in for 4.2 light-years. At 17 kilometers per second, the travel time in seconds is t_seconds equals 4.0 times 10 to the power of 13 kilometer, divided by 17 kilometers per second. Divide the 4.0 by 17 first. 4.0 divided by 17 almost equal to 0.235294. Then attach the power of 10. 0.235294 times 10 to the power of 13 equals 2.35294 times 10 to the power of 12 seconds. If you prefer long division, 40 divided by 17 is equal to 2 with 6 left over. Bring down zeros repeatedly and you'll land at the same tilde 2.35 trillion seconds. Convert seconds to years. A Julian year, 365.25 days, contains 31,557,600 seconds. That's 365.25 times 24 times 60 times 60 is equal to 31,557,600. Check the multiplication stepwise. 24 times 60 is equal to 1,440. 1,440 times 60 is equal to 86,400 seconds per day. 86,400 times 365 is equal to 31,536,000. Add the quarter day. 86,400 divided by 4 is equal to 21,600. So 31,536,000 plus 21,600 is equal to 31,557,600. Now divide 2.35294 times 10 to the power of 12 by 3.15576 times 10 to the power of 7. First divide the coefficients. 2.35294 divided by 3.15576 almost equals 0.746, since 3.15576 times 0.746 almost equals 2.354. Then subtract exponents on the powers of 10. 10 to the power of 12 divided by 10 to the power of 7 equals 10 to the power of 5. Combine them, about 0.746 times 10 to the power of 5 years, which is 74,600 years. If we use the slightly larger, more precise 4.24 light-years and Voyagers, precise tilde 17.0 km/s, you get a figure closer to tilde 75,000 years. That's the famous order of magnitude answer. On the timeline of human culture, it's not a trip, it's a saga carved into geology. There's something instructive about how little the answer budges when you tweak the inputs. Suppose you take Voyager 1 speed and round up generously to 17.5 km per second. Do the same computation. 4.0 times 10 to the power of 13 divided by 17.5 equals 4.0 divided by 17.5 times 10 to the power of 13 equals 0.228571 times 10 to the power of 13 equals 2.28571 times 10 to the power of 12 seconds. Divide by 31,557,600 seconds per year and you get tilde 72,500 years. Trim a few kilometers per second and the time stretches. Add a few and it barely shrinks. The curve is cruel because you're 1,000 times too slow. Shaving or adding 1 or 2 kilometers per second matters as much as swapping one shoe for another in a marathon you're running in molasses. Scale helps this land emotionally. Imagine you launch a Voyager to Proxima every century and you keep doing it for all of recorded history, roughly 5,000 years, placing 50 such silent needles on the same trajectory. The first one still won't arrive for about 70 millennia. That means the very oldest, the very first craft you sent, the one whose launch would be mythology by the time your 50th leaves, is still tens of thousands of years from ringing the cosmic doorbell. Meanwhile, the last in line trails by only a few hundred years, so they'd all arrive bunched in an era of our future that is alien past imagining. Even epic feats of speed inside the solar system barely tickle the interstellar clock. The Parker Solar Probe, in its perihelion sprints, reaches more than 190 km per second, over 10 times faster than Voyager's cruise. Lock that speed in, pretend you could maintain it straight and level forever, and you still face roughly 4.0 times 10 to the power of 13 km divided by 190 km per second, almost equal to 2.105 times 10 to the power of 11 seconds. Divide by 31,557,600 to get tilde 672 years. That's jaw-dropping improvement. Yes, but it still reads like a ledger entry from antiquity. Obelisks erode. Empires ash. Languages molt. Your fast ship keeps going. People sometimes respond to these timescales with a clever workaround. What if you don't aim for arrival? What if you aim for a flyby, coast through the Proxima system at full clip, snap pictures, fire off data, and sail on into the night? That cuts out deceleration, the half of the journey that would otherwise demand as much energy as the speed up, and it's a smart trade for a probe. But the timeline still slumps in the same place. A 75,000-year flyby is just as useless for any society's planning as a 75,000-year arrival. The mission becomes a bottle tossed in a time ocean whose other shore is a future not only without you, but without your grandchildren's grandchildren's grandchildren's. You get the idea. The tyranny here isn't just distance, it's the square cube of energy versus speed. Kinetic energy scales with the square of velocity. Doubling speed requires 4 times the energy. To boost from 17 km per second to, say, 170 km per second, 10 times faster, multiplies the energy requirement by 100. Going to 0.1 c, tilde 30,000 km/s, multiplies it by a factor on the order of open parenthesis 30,000 divided by 17 close parenthesis squared, which is roughly 1,764.7, caret 2 almost equal to 3.11 million. That's for the same mass. If your craft is larger or carries shielding, food, humans, or deceleration propellant, the energy line item balloons further. This is why just a bit faster at interstellar scale translates into civilization-level energy in the budget. There's also the quiet assassin of attrition. For a spacecraft meant to last tens of thousands of years, every component, memory, bearings, solder joints, sealants, lubricants, structural members, must shrug at millennia of thermal cycling, radiation damage, and micrometeoroid hits. Any onboard clock will drift. Any battery will decay. Any antenna pointing error will amplify. The coherence and power of your transmitter must survive ages, while the receiving civilization back home must not only still exist but also still maintain the deep space network, or its successor, still decode your antique protocols, and still speak the institutional language that remembers what this small, cold machine is. Voyager's triumph isn't only that it got where it is, it's that it stayed alive long enough to tell us about it. Stretch long enough to 75,000 years and the phrase stops meaning anything we recognize. You might counter, why not a relay chain? Small beacons dropped along the route every few hundred AU to help navigation, boost comms, and correct for drift. The math again is heartless. A few hundred AU is still less than 1,000th of the way, which means you'd need hundreds of beacons for a single corridor to a single star. Each one must survive for a slice of geologic time. And remember, Proxima is the nearest. The galaxy's median distances are worse. A one-off heroic chain to one target might be thinkable for a Type I+ civilization on the Kardashev scale. A mesh across dozens of stars is a Type II fever dream. The cultural dimension is equally unforgiving at Voyager speeds. A human project that takes 10 years has a project manager. 100 years, a dynasty. 1,000 years, a priesthood. At 10,000 years, you're into the territory of living myths. Meaning replaces method. The continuity you need to shepherd a mission that long is not engineering continuity but civilizational continuity. Stability of institutions across epochs that historically grind everything down. The cathedrals of Europe took centuries. They succeeded not because a single plan persisted in a drawer, but because successive generations reimagined, recommitted, and rebuilt. If we ask for interstellar voyages at Voyager speeds, we're asking for cathedral thinking with a timeline that makes Notre Dame look like a weekend craft. There's an important, sobering clarity in all of this. Crossing the heliopause is not the same as going to the stars. Voyager proved we can exit the sun's protective bubble. It did not prove that, with more patience, we can simply continue on to Alpha Centauri. The orders of magnitude left over are not clerical errors to be fixed by budget increases. They are physics and scale. They demand new propulsion families, nuclear pulse, fusion, beam-driven sails, antimatter, or breakthroughs we haven't written down yet. The Voyager calculation is the reason those exotic ideas are not luxuries but necessities if the goal is interstellar travel on human timescales. And yet, the calculation delivers a strange gift. It gives us a clean, crisp criterion for seriousness. If your interstellar concept can't beat 17 kilometers per second by 2 or 3 orders of magnitude, it isn't actually about the stars. It's about very long-range solar exploration, Oort cloud surveys, or romantic gestures to future archaeology. There's nothing wrong with those. Indeed, they're noble, but they're not a path to Proxima in a lifetime. The math refuses to flatter us. It doesn't care about hopes or headlines. It only says, if you want decades instead of ages, multiply your speed by hundreds to thousands. If you want meaningful return within a career, aim at 1/10 the speed of light and build an energy economy to match. Lay the numbers out, then, and accept their verdict. At Voyager's pace, you need roughly 75,000 years to traverse the 4.2 light-year gap. With a 10-fold speed up, you still need around 7,500 years. At a 100-fold speed up, 1,700 kilometers per second, about 750 years. Only when you reach 1,000-fold speed up, 17,000 kilometers per second, about 5.7% of light speed, do you cut the trip to the length of recorded history. That is the mountain we must climb. It's not a cliff, it's a slope. But it rises for a very long time. And this is why telling the truth about Voyager 8 travel times isn't an exercise in pessimism. It's a compass. It points us away from wishful thinking and toward the very specific, very hard work that actually changes the map. Propulsion that laughs at chemical energy, materials that sip vacuum for breakfast, autonomy that can parent itself for decades, and energy infrastructures measured not in megawatts but in gigawatts and terawatts delivered cleanly and controllably. The stars are not offended by our slowness. They'll wait. The question is whether we are willing to pay the price the distance politely, indifferently charges. Chemical rockets have carried us from the surface of the Earth to the Moon, to the outer planets, and even launched the Voyager spacecraft themselves. They have been the workhorses of the space age, the dependable engines that turned our species into one that can step into orbit and explore other worlds. But when the conversation shifts to interstellar travel, chemical propulsion suddenly looks like a candle flame trying to light up a continent. The fundamental problem isn't that chemical rockets don't work. They work brilliantly for short, high-thrust bursts and for getting heavy payloads out of Earth's gravity well. It's that they are tragically inefficient for the kinds of speeds and energy budgets required to go beyond the solar system. The reason for this limitation is baked into the physics of rockets themselves. Rockets obey what's called the Tsiolkovsky rocket equation, which relates the change in velocity, or delta V, a rocket can achieve to three things: the effective exhaust velocity of the propellant, the mass of the rocket when full of fuel, and the mass after the fuel is expended. In simplified form, the higher your exhaust velocity, the better. The problem? For chemical propulsion, the controlled combustion of fuel like hydrogen and oxygen, the exhaust velocity tops out at just a few kilometers per second. Even the most efficient chemical rockets operating in vacuum, like the Space Shuttle's main engines, reach an exhaust velocity of about 4.5 kilometers per second. That number is tiny compared to what's required for interstellar journeys. To put this in perspective, Voyager 1 is moving at about 17 kilometers per second relative to the Sun, and that speed was achieved only after using Jupiter and Saturn for gravitational assists. If Voyager had relied solely on chemical propulsion to reach those speeds, it would have needed a completely impractical fuel-to-payload ratio. A rocket trying to accelerate even a modest spacecraft to 1/10 the speed of light using nothing but chemical fuel would require so much propellant that the fuel tank would be larger than entire planets. This isn't poetic exaggeration, it's what the math says. The exponential nature of the rocket equation ensures that for every small increase in speed you want, you need disproportionately more fuel. By the time you're aiming for a few percent of light speed, the requirement balloons to absurd levels. Let's imagine we wanted to accelerate a spacecraft to even 0.01 c, or 1% the speed of light. That's about 3,000 kilometers per second, already hundreds of times faster than Voyager. A chemical rocket simply cannot get there because its exhaust velocity is only a few kilometers. The rocket equation says your delta V is equal to your exhaust velocity multiplied by the natural logarithm of your mass ratio. If your exhaust velocity is only 4.5 kilometers per second, there's no way to achieve 3,000 kilometers per second, no matter how much fuel you pile on, because the logarithm grows very slowly. You would end up needing a mass ratio, fuel to payload, on the order of 10 to the power of 100 or more, a number so large it's physically impossible. Even if you turned Jupiter itself into a propellant tank, you wouldn't come close. Chemical rockets also suffer from another harsh reality: energy density. The chemical bonds in fuel like hydrogen and oxygen release a certain amount of energy per kilogram when they burn. It's a lot compared to everyday experiences, but it's minuscule compared to nuclear or relativistic energy sources. Hydrogen-oxygen combustion releases about 13 million joules per kilogram of propellant. In comparison, nuclear fission releases around 90 billion joules per kilogram of uranium fuel, and nuclear fusion can theoretically release on the order of hundreds of billions of joules per kilogram. Antimatter annihilation, the most extreme case, releases about 9 times 10 to the power of 16 joules per kilogram, orders of magnitude higher still. The difference is staggering. Chemical energy is a toy compared to the energy scales required for interstellar travel. Even if we tried to optimize chemical propulsion to its theoretical maximum, squeezing every last drop of performance out of exotic propellants, the improvement would still be incremental. Liquid hydrogen and liquid oxygen, methane, kerosene, even hydrogen fluoride mixtures, all of them hover in the same neighborhood of performance, within a factor of 2 or so. There's simply no path within chemistry to leap from single-digit kilometers per second exhaust velocity to the thousands of kilometers per second needed for starflight. The chemistry is locked by the laws of thermodynamics and atomic bonding energies. There's no trick left to discover. Chemical rockets, then, become relegated to the role of first-stage technologies. They are essential for getting us off the ground and perhaps for moving around the solar system efficiently, especially with creative use of gravity assists and orbital refueling. But once the discussion shifts to breaking through the speed barrier that separates solar system travel from interstellar travel, they fade from the picture entirely. The very best they can do is give us a head start, pushing us into space where other propulsion methods, nuclear, solar sail, or otherwise, must take over. Another way to grasp the problem is to ask, how much chemical fuel would it take to send even a small spacecraft to Proxima Centauri in, say, 10,000 years? That would require a cruise velocity of about 13,000 kilometers per second, still only about 4% the speed of light. If you try to build a chemical rocket for this mission, the required mass ratio between fuel and payload grows so wildly that you'd need more fuel than could ever be manufactured on Earth. It isn't just impractical, it's fundamentally impossible with chemical reactions. The rocket equation slams the door shut. This realization is why space visionaries as early as the 1940s began considering nuclear alternatives. Engineers and scientists knew that chemical rockets could get us to orbit, maybe even Mars, but they could never get us to the stars. Wernher von Braun himself admitted this limitation when thinking about interstellar concepts. Even the Saturn V, the most powerful chemical rocket ever built, produced an astonishing 34 million newtons of thrust, but it was entirely unsuited for anything beyond Earth's neighborhood. The Saturn V could barely nudge a few humans to the moon and back. A Saturn V-style approach scaled up 1,000,000 times still wouldn't dent the problem of interstellar flight. The phrase speed barrier isn't just metaphorical. It describes a fundamental bottleneck. With chemical propulsion, we're trapped at a fraction of the speeds we need. Rockets as we know them are magnificent for escaping Earth's atmosphere and hopping between nearby worlds, but they will never carry us to the stars. To do that, we must leap to entirely different paradigms of propulsion: nuclear, fusion, antimatter, or even the speculative bending of space-time itself. Chemical rockets built our bridge into space, but they will not take us across the ocean of interstellar distances. If chemical rockets are the first rung on the ladder of space exploration, then nuclear propulsion represents the next bold step upward, a step that could, in theory, take us far beyond the reach of Mars and toward the outer planets, even potentially setting the stage for interstellar. Precursors. Nuclear propulsion comes in several forms, each with its own strengths, challenges, and history, but all of them are rooted in one basic truth. Nuclear reactions release millions of times more energy per unit of fuel than chemical combustion ever could. That energy density advantage is what makes nuclear propulsion such an enticing possibility for deep space missions. The first major concept is nuclear thermal propulsion, NTP. In this system, you don't rely on chemical energy at all to heat your fuel. Instead, you use a compact nuclear reactor as your furnace. The reactor heats a lightweight propellant, most often liquid hydrogen, to extremely high temperatures, and then the hydrogen is expelled through a nozzle to produce thrust. It works a lot like a conventional rocket engine, but instead of burning hydrogen with oxygen, you simply run it through the blazing hot core of a reactor. The result is a specific impulse, essentially a measure of efficiency, about twice that of the best chemical rockets. Chemical rockets can achieve around 450 seconds of specific impulse, while nuclear thermal rockets could theoretically achieve around 900 seconds or more. That may not sound like a huge leap, but in space travel, doubling your efficiency changes the game. With nuclear thermal propulsion, missions to Mars could be cut from roughly 9 months to perhaps 4 to 6 months, drastically reducing the radiation exposure astronauts would face on the journey. For interstellar travel, NTP doesn't come close to what we'd need. It's still far too slow, but it represents a vital stepping stone technology. It's a way of building the engineering experience and nuclear safety expertise required to field even more ambitious systems later. NASA and DARPA are currently revisiting NTP concepts, with projects like Draco aiming to test nuclear thermal propulsion in orbit within the next decade. That demonstrates that nuclear ideas are no longer just science fiction, they're edging toward real-world hardware. Then there is the bolder and far more powerful idea: nuclear pulse propulsion, exemplified by the famous Project Orion of the late 1950s and early 1960s. Orion remains one of the most audacious spaceflight concepts ever seriously studied. The idea was deceptively simple yet staggering in execution. What if you propelled a spacecraft not with a steady push of fuel, but by detonating a series of small nuclear bombs behind it? The ship would have a massive, shock-absorbing pusher plate at the back. Each bomb would explode, the plate would absorb the blast's energy, and the ship would be kicked forward. Repeat this thousands of times, and suddenly you have a craft that could, in theory, reach a significant fraction of the speed of light. The numbers for Orion were tantalizing. Calculations suggested that a ship powered by nuclear pulse propulsion could reach about 10% the speed of light, far beyond anything conventional rockets could achieve. That would bring interstellar travel within the realm of possibility, at least over timescales of a few decades or centuries instead of tens of thousands of years. A spacecraft using Orion technology could weigh thousands of tons, large enough to house human crews, supplies, and perhaps even rotating habitats for artificial gravity. It wasn't just a probe concept, it was a vision of starships. Yet Orion faced insurmountable challenges. Detonating nuclear bombs in Earth's atmosphere, or even just outside, it was unthinkable once the dangers of radioactive fallout became fully clear. The safety concerns would be enormous. Designing a ship to survive repeated nuclear blasts, managing the logistics of carrying thousands of nuclear devices, and protecting the crew from radiation were daunting engineering challenges. And, of course, the public perception of nuclear bomb-powered spaceships would be a public relations nightmare. Still, Orion refuses to die entirely. Enthusiasts and futurists keep reviving the idea, sometimes in modified forms. For example, there are proposals for using fusion micro-explosions instead of fission bombs, or confining the blasts within magnetic fields to direct the energy more efficiently. These offshoot concepts, such as Project Daedalus and Project Icarus, blend elements of Orion with fusion propulsion, which we'll discuss later. But at its heart, Orion remains a symbol of what nuclear energy could, in theory, make possible. Interstellar voyages measured in centuries instead of eons. There are also intermediate nuclear propulsion concepts. Nuclear electric propulsion, NEP, for instance, involves using a nuclear reactor not to heat propellant directly but to generate electricity, which then powers ion or Hall effect thrusters. These thrusters expel ions at very high velocities, giving them extremely high efficiency, though at very low thrust. A nuclear-powered ion drive could keep firing for years or decades, slowly but steadily accelerating a spacecraft to impressive speeds. While NEP wouldn't get us to the stars quickly, it could be a highly practical technology for exploring the outer solar system. Missions to Uranus, Neptune, and even Kuiper belt objects could be dramatically improved by pairing nuclear reactors with electric propulsion systems. What all these nuclear concepts have in common is the leap in energy density. They break us free from the tyranny of chemistry and its paltry energy yields. They open the door to propulsion systems that could realistically shorten mission times, expand payload capacity, and maybe one day, if scaled boldly enough, take humans beyond the solar system. Nuclear propulsion is not a magic bullet. It comes with risks of radiation, complex engineering demands, but it is one of the few propulsion categories that bridge the gap between current technology and the dream of interstellar flight. When you consider that the stars are so far away that chemical rockets barely get us out of the cosmic driveway, nuclear propulsion feels like the first adult step toward the stars. Whether through thermal rockets shaving years off missions, electric propulsion giving us efficient long-duration thrust, or pulse propulsion hinting at genuine starships, nuclear systems remind us that our future in space will almost certainly require tapping the immense power locked inside the atom. Among the most elegant and futuristic ideas for interstellar propulsion is the concept of solar sails, or more broadly, light sails. Unlike rockets, which must carry their own fuel, light sails rely on the pressure of photons, particles of light, pushing against a large, reflective surface. It's a propulsion method that requires no onboard propellant, which immediately solves one of the biggest problems of interstellar travel, the rocket equation. Instead of lugging an impossibly massive fuel tank across the void, a sail-powered spacecraft could, in theory, be accelerated indefinitely as long as light continues to strike it. This idea turns sunlight, or even directed laser beams, into a cosmic wind that can carry tiny ships to a significant fraction of the speed of light. The physics behind it is surprisingly simple. Even though photons are massless, they still carry momentum. When a photon reflects off a surface, it transfers a tiny push. On Earth, the effect is so minuscule that it's undetectable in everyday life. But in the frictionless vacuum of space, and spread across a sail hundreds or thousands of meters wide, those tiny pushes add up. The result is continuous, fuel-free acceleration. Unlike rockets that burn for minutes or hours and then coast, a solar sail can keep building speed for years or even decades, limited only by the availability of light and the durability of its materials. Solar sailing isn't just a theoretical concept. We've already tested it. Japan's Ikaros spacecraft, launched in 2010, became the first successful demonstration of solar sail technology. It deployed a 14-meter-wide sail and used sunlight alone to adjust its trajectory, proving that photon pressure is a viable form of propulsion. The Planetary Society's LightSail project has also launched multiple small spacecraft with reflective sails, further validating the technology. These missions are modest compared to interstellar ambitions, but they show that the principle works. Now, when we start dreaming bigger, about leaving the solar system and actually reaching nearby stars, the idea becomes even more exciting. The natural light of the sun can push a sail outward, but its strength diminishes with distance. By the time a spacecraft reaches the outer solar system, sunlight is so weak that acceleration becomes negligible. That's where the concept of laser-driven sails comes in. Instead of relying solely on the sun, you build gigantic ground-based or space-based laser arrays and focus intense beams on the sail. Unlike sunlight, the laser doesn't weaken with distance from Earth. It keeps pushing as long as you maintain the beam. This is the basis for the Breakthrough Starshot initiative, one of the most ambitious and realistic interstellar probe concepts currently under study. Backed by figures like Yuri Milner and Stephen Hawking, the plan envisions building a massive array of powerful lasers on Earth, combining their beams into a coherent pulse, and using it to accelerate tiny, gram-scale spacecraft with ultra-thin sails. These starships could, in theory, be pushed to about 20% the speed of light. At that velocity, they could reach Proxima Centauri in just over 20 years, a staggering improvement compared to the tens of thousands of years it would take Voyager at its current speed. The scale of such a project, however, is monumental. The laser array would need to generate tens of gigawatts of power, comparable to the output of the largest power plants on Earth. The sail itself would need to be incredibly light, perhaps only a few atoms thick, and yet able to withstand the immense acceleration forces without tearing apart. The spacecraft riding on it would have to be shrunk down to the size of a microchip, carrying sensors, cameras, and communication equipment so lightweight and efficient that they could survive the journey and send back data across light years. The engineering challenges are staggering, but none of them require breaking the laws of physics. It's all about materials science, power infrastructure, and precision control. Solar sails also introduce unique challenges in navigation and durability. A spacecraft moving at 20% the speed of light would collide with interstellar dust grains at devastating energies. Even tiny particles could puncture or shred a delicate sail. Radiation would bombard the craft constantly, and communicating across light years with a probe only a few grams in size would require extraordinary ingenuity. Still, when compared to the impossibility of using chemical rockets for interstellar missions, sails feel like a genuine pathway forward, one that could, at least for robotic probes, be achievable within this century. What's fascinating about solar and laser sails is their scalability. At small sizes, they're ideal for lightweight probes. But one could also imagine larger versions for crewed ships, though the engineering challenges would multiply. A sail kilometers across, perhaps assisted by powerful lasers stationed in orbit around the Sun, could one day accelerate a human habitat to a fraction of light speed. Science fiction often imagines great silver sails unfurling in the void, slowly carrying pioneers into interstellar space. For now, reality points toward tiny probes, but the principle is the same. Another intriguing aspect is that light sails might also be an efficient way to decelerate at the destination. A probe approaching Proxima Centauri at 20% the speed of light can't just slam on the brakes. It has no onboard fuel. But if it deploys its sail in reverse, it could theoretically use the light and stellar wind from Proxima's star to slow down, albeit very gradually. More exotic ideas suggest using magnetic sails or plasma parachutes to interact with the interstellar medium for deceleration. These remain speculative, but they show how versatile sail concepts can become when combined with clever physics. Ultimately, solar sails represent one of the most promising near-term methods of interstellar exploration, not for humans yet, but for robotic scouts. They are elegant, efficient, and grounded in well-understood physics. They shift the problem of interstellar travel from carrying impossible amounts of fuel to building immense infrastructure here at home, like laser arrays and precision spacecraft manufacturing. For the first time, they allow us to realistically imagine sending machines to another star within the lifetime of people alive today. That is revolutionary. Fusion drives represent perhaps the most tantalizing balance between feasibility and ambition when it comes to interstellar travel. Unlike antimatter engines or warp drives, which currently exist far more in theory than in practical design, fusion propulsion has a strong foundation in physics and ongoing research in energy production here on Earth. Fusion is the process that powers the stars themselves, the reaction in which atomic nuclei, usually isotopes of hydrogen such as deuterium and tritium, are forced together under extreme temperatures and pressures, releasing enormous amounts of energy. If humanity can learn to tame this reaction and use it not just to generate electricity on Earth but to propel spacecraft across the cosmos, it could become our golden ticket to the stars. The allure of fusion propulsion is easy to understand. A single gram of fusion fuel can release as much energy as tons of chemical rocket propellant. Fusion has an energy density millions of times higher than chemical combustion, which makes it one of the only realistic candidates for powering starships at a significant fraction of the speed of light. Unlike fission, which splits heavy atoms, fusion combines light atoms, and the primary fuels, deuterium and helium-3, are relatively abundant. Deuterium can be extracted from seawater, and helium-3 could one day be mined from the surfaces of the Moon or the gas giants. In principle, we could source the necessary fuels for large-scale interstellar missions from within our own solar system. One of the most famous proposals to use fusion for interstellar travel was Project Daedalus, a bold design developed in the 1970s by the British Interplanetary Society. The idea was to build a massive, two-stage, uncrewed starship capable of reaching Barnard's star, about 6 light-years away, within a human lifetime. Daedalus was designed to accelerate to about 12% of the speed of light, which would reduce the travel time to roughly 50 years, an extraordinary improvement compared to Voyager's 75,000 years. To achieve this, the spacecraft would use inertial confinement fusion. Tiny pellets of deuterium and helium-3 would be bombarded with electron beams, igniting miniature fusion explosions that would be funneled out the back of the spacecraft to produce thrust. The scale of Daedalus was staggering. It was envisioned to weigh about 50,000 tons, most of which was fuel. The engine section alone would have been larger than most skyscrapers. The ship would not have carried humans but rather robotic probes and autonomous systems capable of studying the target star system and relaying information back to Earth. In many ways, Daedalus was less a blueprint for an actual mission and more a proof of concept, a demonstration that, given known physics and foreseeable engineering, interstellar flight within a centroscale timeframe was not impossible. Decades later, a follow-up study known as Project Icarus revisited and updated the Daedalus concept. Engineers and scientists sought to modernize the design, incorporating advances in computing, robotics, and fusion research. The Icarus project explored not just inertial confinement fusion but also magnetic confinement fusion, where magnetic fields trap plasma at high temperatures, allowing sustained fusion reactions. Magnetic confinement is the principle behind experimental reactors like ITER on Earth, though so far humanity has not achieved a sustained, net positive fusion reaction. Icarus also placed greater emphasis on modularity, autonomy, and scalability, imagining fleets of probes rather than one colossal starship. The promise of fusion drives lies in their ability to deliver continuous thrust at high efficiency. Unlike chemical rockets, which burn out quickly, or solar sails, which rely on external photon pressure, a fusion engine could fire for years, steadily pushing a spacecraft to immense velocities. Estimates suggest that with advanced fusion propulsion, reaching 10 to 20% of the speed of light might be possible. At such speeds, nearby stars could be reached in decades to centuries, a timescale within the grasp of civilization-scale projects rather than something requiring millennia. But the challenges are just as immense. The first and most obvious problem is that we still haven't mastered fusion energy for Earth-based power plants. Fusion reactors are notoriously difficult to sustain, requiring temperatures hotter than the core of the Sun and pressures that are difficult to maintain without consuming more energy than the reaction produces. Scaling that technology up, or, more accurately, scaling it down into a rocket engine, adds layers of complexity. How do you ignite and control millions of tiny fusion explosions per second? How do you direct their energy into a focused exhaust stream without melting your engine? How do you protect the spacecraft and its payload from the intense radiation produced by fusion reactions? Then there is the sheer scale of construction. A Daedalus-class vehicle would require industrial capabilities far beyond what we have today, likely demanding in-space assembly using resources mined from asteroids or moons. Building such a craft on Earth and launching it whole would be impossible. Instead, humanity would need to establish a mature spacefaring civilization, capable of harvesting fuels like helium-3 from the outer planets and assembling megastructures in orbit or deep space. Fusion propulsion, in other words, is not a technology that comes first, it is the fruit of a much larger space infrastructure. Despite the obstacles, fusion propulsion remains one of the most credible paths toward the stars. Unlike warp drives or antimatter engines, it doesn't require exotic physics or unobtainable materials. It only requires breakthroughs in plasma physics, reactor stability, and large-scale engineering. Daunting but potentially solvable with enough time, money, and scientific progress. And that's why fusion drives continue to inspire generations of researchers and enthusiasts. They feel like a halfway point between hard science and science fiction, a place where imagination and possibility converge. When we think about the future of interstellar travel, fusion drives symbolize the moment when humanity stops crawling outward with fragile chemical rockets and instead begins to stride with engines worthy of a spacefaring civilization. Whether in the form of a Daedalus-inspired robotic probe, an Icarus-like modular fleet, or some yet undreamed-of design, fusion propulsion could one day carry our machines, and perhaps our descendants, beyond the sun's influence and into the great ocean of the stars. If fusion propulsion represents the practical dream of tomorrow, then antimatter propulsion embodies the wild promise of the far future. A technology so potent that it borders on magical, yet so constrained by our present limitations that it feels like a distant fantasy. Antimatter is often described as the most powerful fuel in the universe, and in a sense, that's absolutely true. When ordinary matter collides with antimatter, the two annihilate completely, releasing pure energy according to Einstein's famous equation, E=mc². Unlike chemical reactions, which convert a tiny fraction of mass into energy, or even fusion, which releases only a small portion of potential mass energy, matter-antimatter annihilation is 100% efficient. Every gram of matter and antimatter converted yields a staggering amount of energy, millions of times greater than what chemical propellants can provide and orders of magnitude beyond fusion's capabilities. To put this into perspective, 1 gram of antimatter reacting with 1 gram of matter would release the energy equivalent of a nuclear bomb. Just a few kilograms of antimatter would be enough to accelerate a spacecraft to relativistic speeds, a fraction of the speed of light, capable of reaching nearby stars within a human lifetime. That's why antimatter engines have fascinated scientists, futurists, and science fiction writers alike. If we could harness them, they might provide the ultimate propulsion system, one powerful enough to make interstellar travel not just theoretically possible, but actually practical. There are several conceptual designs for how an antimatter engine might work. One idea is to trap charged antiparticles, such as positrons or antiprotons, and carefully release them into a reaction chamber where they would collide with normal matter, generating high-energy gamma rays. These gamma rays could then be directed, at least in theory, into a thrust stream by some sort of magnetic or reflective system, propelling the spacecraft forward. Another proposal involves mixing antimatter with a conventional fusion reaction, using the antimatter as a catalyst to trigger and sustain fusion. This hybrid design would reduce the amount of antimatter required, making it more feasible while still leveraging its immense power. But here's where the dream collides with reality. The first and most crushing limitation is simply producing antimatter. Despite decades of research at facilities like CERN, where tiny amounts of antimatter have been created in particle accelerators, the total amount humanity has produced so far is measured in nanograms, billionths of a gram. To accumulate even a few grams, let alone kilograms, would require an unimaginable amount of energy and infrastructure. Some estimates suggest that producing just 1 gram of antimatter could cost hundreds of trillions of dollars at today's efficiencies. In other words, even if we had the perfect antimatter engine sitting in front of us, we simply don't have the fuel to run it. The second challenge is storage. Antimatter cannot come into contact with ordinary matter without annihilating instantly. That means you can't keep it in a tank like gasoline or liquid hydrogen. Instead, it has to be suspended in electromagnetic traps, levitating in a perfect vacuum, isolated from the walls of its container by strong magnetic fields. This is doable for tiny amounts. Particle physicists already use devices called penning traps to confine antiprotons for short periods. But scaling that up to store grams or kilograms for years in the harsh environment of space would be an engineering feat of unprecedented complexity. One tiny glitch, one power failure, and your carefully trapped antimatter would annihilate with its surroundings, releasing catastrophic energy. Then there is the issue of directing the energy. Matter-antimatter annihilation produces high-energy gamma rays, which are incredibly difficult to manipulate. Unlike charged particles, which can be bent and focused with magnetic fields, gamma rays pass through most materials, making it nearly impossible to channel them efficiently into a controlled thrust stream. Without a way to direct the energy, much of it would be wasted or would fry the spacecraft itself. Some designs attempt to use dense materials to absorb the gamma rays and re-radiate their energy as heat, which can then be expelled as plasma. But these methods introduce massive inefficiencies, and the engineering challenges remain daunting. In addition to the technical challenges, there are safety and ethical concerns. Antimatter is not just dangerous, it's the ultimate explosive. A spacecraft carrying even a small supply would effectively be carrying a weapon of unimaginable power, raising concerns about militarization and catastrophic accidents. The thought of storing kilograms of antimatter anywhere near Earth is almost unthinkable. For antimatter propulsion to become a real option, humanity would likely need to develop advanced space-based industries far from our planet, capable of producing, containing, and utilizing antimatter without endangering terrestrial life. Despite all these limitations, antimatter propulsion continues to inspire research, at least on the theoretical level. NASA and other institutions have studied concepts like antimatter-catalyzed microfusion, in which small amounts of antimatter trigger fusion reactions, dramatically reducing the fuel requirements compared to a pure antimatter engine. This hybrid approach might one day offer a compromise between feasibility and performance. Some scientists also speculate that naturally occurring antimatter, trapped in the magnetic fields of planets like Earth and Jupiter, could be harvested. But these reserves are minuscule and would still require technology far beyond what we possess today. So, where does that leave us? Antimatter propulsion is undeniably the most powerful theoretical engine we can currently imagine. It would allow starships to reach relativistic speeds, opening the door to interstellar travel within timescales that humans could endure. But the gap between imagination and reality is enormous. The costs, the engineering challenges, and the sheer impracticality of producing and storing antimatter mean that for now, antimatter drives are more science fiction than science fact. Still, the idea refuses to die, because in the pursuit of the stars, the most extreme ideas often serve as guiding lights, showing us what might be possible if our civilization grows advanced enough. When antimatter engines stretch the limits of engineering, warp drives leap directly into the territory of rewriting physics itself. The most famous of these speculative ideas is the Alcubierre warp drive, a concept proposed in 1994 by theoretical physicist Miguel Alcubierre. Unlike rockets, sails, or even antimatter annihilation, which are all about pushing a spacecraft through space faster and faster, the Alcubierre concept sidesteps the whole problem of propulsion. Instead of moving through space, the idea is to move space itself. The basic principle is elegant and profoundly strange. Since Einstein's relativity forbids objects from traveling faster than the speed of light in their local region of spacetime, why not just contract space in front of the spacecraft and expand it behind? The ship itself doesn't technically exceed the speed of light, it simply rides a warp bubble of curved spacetime that carries it forward. Within the bubble, the spacecraft is essentially at rest relative to its surroundings, so it never breaks relativity's rules. But from an outside perspective, the bubble can move across interstellar distances at superluminal speeds. In theory, such a warp drive could allow us to cross the gap to Proxima Centauri in a matter of weeks or months instead of tens of thousands of years. This concept is so compelling that it has inspired countless discussions, simulations, and even serious studies by institutions like NASA's EagleWorks laboratory. But as soon as you dive deeper, the immense obstacles become apparent. To generate a warp bubble, Alcubierre's equations require a form of negative energy or exotic matter, something that, as far as we know, does not exist in usable quantities. Unlike ordinary matter, which has positive energy density, exotic matter would create repulsive gravity, a kind of anti-gravity effect that could bend spacetime in the necessary way. Without this exotic material, the bubble cannot be formed, and the amounts required are staggering. Early estimates suggested that to create a warp bubble big enough to carry a modest-sized spacecraft, you would need as much negative energy as the mass energy of the entire observable universe. Later refinements reduced that number to the energy equivalent of a few solar masses, and even more optimistic studies suggested maybe it could be done with the energy equivalent of a few Jupiter masses. But even that is far, far beyond anything humanity could realistically harness. We struggle to generate enough energy to power a continent, let alone warp spacetime across interstellar distances. Another challenge lies in stability. Even if exotic matter exists and could be harnessed, warp bubbles may be inherently unstable. Some theoretical models suggest that the moment the bubble is created, it would collapse almost instantly, destroying the spacecraft inside. Others indicate that the bubble might trap enormous amounts of radiation at its edges, frying anything within it the instant it comes to a stop. The mathematics of general relativity in this regime are incredibly complex, and while Alcubierre's solution is mathematically valid, it may not correspond to a physically realizable phenomenon in our universe. There's also the issue of causality. Faster-than-light travel carries with it the risk of violating the order of cause and effect. If information or objects could be transmitted faster than light, paradoxes might arise, events happening before their causes, timelines looping back on themselves, and so on. Many physicists believe that the universe has built-in safeguards against this kind of violation, and the absence of observable superluminal travelers in our skies could be a hint that warp drives simply cannot exist in practice. Still, warp drives occupy a unique space in the human imagination. Unlike pure fantasy, they are rooted in actual mathematics, solutions to Einstein's equations. That makes them different from magical teleportation or purely fictional devices. They are a tantalizing what-if, dangling at the edge of physics as we know it. Even if the Alcubierre model turns out to be impossible, exploring these ideas pushes the boundaries of our understanding. Research into exotic matter, quantum vacuum fluctuations, and the nature of spacetime might reveal new insights into the structure of the cosmos. Who knows? Today's impossible might become tomorrow's engineering problem. NASA's interest in warp drives shows this very tension between fantasy and possibility. In 2012, Harold White and his team at EagleWorks proposed a modified version of Alcubierre's design that drastically reduced the energy requirements by altering the shape of the warp bubble. Instead of a massive spherical field, a more toroidal or donut-shaped bubble might work with far less exotic matter. The numbers are still absurdly high, but the mere fact that they could be reduced at all gave hope that maybe, just maybe, the universe is less rigid than we thought. And beyond the technicalities, warp drives capture the essence of why we dream of interstellar travel in the first place. They embody the idea that human ingenuity might one day outwit the universe's speed limits, that we are not forever bound to slow journeys through endless gulfs of space. They take the yearning to explore and magnify it into a vision of instant connection across light years, a cosmic railroad linking star to star. Of course, sober reflection reminds us that we are nowhere near achieving such a feat if fusion drives require centuries of progress. Warp drives may require revolutions in physics itself, discoveries as profound as relativity or quantum mechanics were in their time. But whether they remain forever speculative or someday inch toward reality, warp drives remind us to keep our minds open. After all, many things once thought impossible, flight, electricity, space travel itself, became possible through persistence and imagination. If nothing else, warp drives expand the scope of our dreaming, pushing us to ask questions about the very fabric of space and time. If warp drives ask us to rewrite the laws of physics, generation ships ask us to rewrite the way we think about human civilization. The idea of a generation ship comes not from exotic energy or faster-than-light speculation, but from a sober acceptance of the distances between the stars. If we cannot bend space or leap across light years in an instant, perhaps we can simply take the long road, an unimaginably long road. A generation ship would be a colossal spacecraft, essentially a self-contained world, where entire communities live, work, raise children, and die, all while the vessel slowly drifts toward another star. The people who launch such a ship would never arrive. Their children wouldn't arrive. Maybe not even their grandchildren. Instead, the hope would rest on dozens of generations maintaining the mission until, centuries or millennia later, their descendants finally reach the destination. The concept has been a favorite in science fiction for decades, appearing in novels, films, and academic studies. But beneath the fiction lies a very real line of thought. If we cannot beat the laws of physics, maybe we can work within them. At current technological levels, even if we had a propulsion system far superior to chemical rockets, say, nuclear pulse propulsion or a powerful fusion drive, the journey to the nearest star would still likely take hundreds of years. That's far too long for a single crew to survive, but not beyond the scale of human civilization itself. After all, Humans have lived in settled agricultural societies for about 10,000 years. Why couldn't we maintain a spacecraft society for 1,000? Designing such a ship is a monumental challenge. First, their size. A vessel that must support human life for centuries cannot be a cramped capsule like Apollo, or even the International Space Station. It would need to be vast, containing not just habitats but farms, water recycling systems, manufacturing capabilities, and cultural spaces. Think of it less like a ship and more like a mobile city, or even a small planet. Concepts like O'Neill cylinders, massive rotating habitats that use centrifugal force to simulate gravity, come into play here. A generation ship would likely need rotating habitats kilometers across to keep its inhabitants healthy over centuries. Food and resources are another issue. On Earth, agriculture depends on ecosystems, soil, weather, pollinators, and countless interconnected factors. On a ship, all of that would have to be artificially maintained. Hydroponics, vertical farming, and genetically engineered crops might provide some answers, but the system would need to be virtually perfect. A single failure could threaten not just one harvest, but the survival of the entire community. Likewise, recycling of water, air, and nutrients would have to be flawless. Over hundreds of years, even tiny inefficiencies could accumulate into catastrophic shortages unless carefully managed. Then there is the human factor. How do you maintain morale, purpose, and social stability across generations who will never see the mission's end? The people born aboard would not have chosen the journey, yet their lives would be defined by it. Some might feel trapped, others resentful, and still others apathetic. For the mission to succeed, the culture of the ship would need to instill a powerful sense of continuity, duty, and shared destiny. Education would play a central role, ensuring that each new generation understood both the practical skills required to run the ship and the philosophical reason for their existence. Art, traditions might all evolve in unique ways aboard such a vessel, binding the community together across the centuries. Ethical questions also arise. Is it fair to consign future generations to a life aboard a spacecraft without their consent? The original crew may launch with noble intentions, but their great-great-great-grandchildren may not share the same values. They will not have chosen to be born in a steel world drifting through the void, yet they will have no other choice. This raises profound questions about freedom, destiny, and the responsibilities of one generation to another. Still, for all the challenges, generation ships have a certain elegance. Unlike warp drives, they don't require exotic physics. Unlike antimatter drives, they don't require impossibly rare fuels. They are, in principle, achievable with known science, albeit stretched to its absolute limits. The hardest parts are not propulsion or engineering, but sociology and psychology. Can we build not just a ship, but a society resilient enough to endure the longest journey ever attempted? One possible compromise is the idea of a semi-generation ship, where life extension technologies or cryogenic sleep, topics we'll explore shortly, reduce the number of generations needed. If humans could live for centuries, or if crews could sleep for decades at a time, the burden might be lighter. But even then, the vessel itself would need to endure, a home that outlasts its creators. In the end, generation ships force us to think of interstellar travel not as a sprint, but as a marathon, an epic relay race across the ages. They transform space exploration from a technological challenge into a civilizational one. And while they may seem daunting, perhaps they are also deeply human. After all, every generation on Earth is already part of a journey begun long before us, and destined to continue long after we are gone. A generation ship simply makes that reality literal, enclosing the story of humanity within the walls of a star-bound ark. If generation ships imagine humanity building floating cities that carry countless generations across the void, cryosleep offers a very different solution, one that sidesteps the problem of maintaining entire societies over centuries by simply putting the travelers to sleep. It's one of the most familiar tropes in science fiction, but also one of the most intriguing possibilities. Instead of living out their lives on the way to another star, astronauts would enter a deep state of hibernation, a kind of biological pause button, only to be awakened when they reach their destination. In this way, a single crew could make the voyage without the need for thousands of descendants to continue the mission. The appeal is obvious. Imagine boarding a spacecraft, climbing into a pod, closing your eyes, and waking up hundreds of years later orbiting a new sun. To the sleeper, the journey would be instantaneous, a bridge across time. From a mission planning perspective, it would remove countless challenges. No need for vast farms to feed multiple generations, no need for complex systems to maintain order over centuries, no need to prepare children for a life they did not choose. Instead, the ship could be largely automated, quietly carrying its sleeping passengers across the darkness. But turning this elegant vision into reality is an enormous challenge. On Earth, some animals naturally enter states of hibernation or torpor, dramatically slowing their metabolism to survive periods of scarce food or harsh climates. Bears, for instance, can hibernate for months, reducing their heart rate, conserving energy, and emerging in the spring still healthy. Certain frogs can even freeze solid and then thaw back to life. These examples show us that nature already has pathways to deep biological suspension. Humans, however, lack such an ability. Our bodies are not built to simply switch off for decades. Our cells need constant energy, our organs need constant function, and shutting those processes down risks permanent damage. That said, medical science has already taken the first steps toward artificial hibernation. Hospitals sometimes use therapeutic hypothermia, cooling a patient's body to reduce metabolic demand during surgery or after cardiac arrest. By lowering body temperature just a few degrees, doctors can buy precious time for the brain and heart, preventing tissue damage when blood flow is interrupted. In experimental contexts, scientists have managed to put small animals like mice into extended states of torpor by manipulating brain chemistry or adjusting oxygen and carbon dioxide levels. These hints suggest that it might be possible, at least in theory, to induce similar states in humans. NASA has studied this possibility seriously. For missions to Mars, which could take many months, the space agency has considered placing astronauts into a kind of stasis for the bulk of the trip. Instead of needing to carry large supplies of food, water, and exercise equipment for awake and active crew members, the spacecraft could be smaller and more efficient. In 2014, a NASA-funded study explored putting astronauts into torpor for up to 2 weeks at a time, with the goal of extending that to months or longer. While far from the deep, decades-long hibernation needed for interstellar travel, it's a starting point that shows scientists are taking the idea seriously. The benefits extend beyond resource savings. Long-term space travel poses significant psychological challenges. Being confined in a ship for years with the same crew can lead to stress, isolation, and conflict. Cryosleep could eliminate many of these issues. It would also protect the crew from exposure to cosmic radiation for at least part of the journey, since shielding a smaller, inactive volume might be more feasible. However, the technical obstacles remain daunting. Prolonged inactivity in humans leads to muscle atrophy, bone density loss, and immune system weakening. Even astronauts on the International Space Station, who exercise daily, experience these problems after just months in microgravity. How would a hibernating body fare after decades? Would the body waste away irreversibly? Would organs degenerate? Even if the metabolism were slowed, some cellular processes would continue, and damage could accumulate. There's also the challenge of waking up. If someone is in stasis for 100 years, how do you ensure they can be safely revived? What if there's a system failure, a power outage, or a malfunction in the pod? The crew would be helpless to repair or intervene. Automation would need to be near perfect, with redundancy upon redundancy to ensure that a glitch doesn't doom everyone aboard. On top of that, there are philosophical and psychological concerns. Even if the technology works, what would it mean to go to sleep knowing you might never wake up? Or that if you do, the world you left behind will be centuries in the past, your loved ones long gone, your culture transformed beyond recognition? Cryosleep is, in a sense, a form of time travel, except unlike science fiction time machines, it only moves you forward, and only by erasing your conscious experience of the intervening years. Some might embrace this, seeing it as a way to escape the burden of waiting. Others might find it terrifying. Still, for all its difficulties, cryosleep offers a bridge between the impossible and the achievable. We may never warp space or build generation ships the size of continents, but we might someday master the art of putting the human body into safe, controlled stasis. Advances in regenerative medicine, stem cell therapy, nanotechnology, and cryogenics all point toward possibilities that could make this a reality. If humans can one day hibernate like bears, or like the fictional crews of interstellar arcs, then the stars might not feel quite so distant. And perhaps there's another dimension to consider. If we solve cryo-sleep, it won't just be useful for star travel. It could revolutionize medicine here on Earth, buying time for patients awaiting transplants, protecting the severely injured until they can be treated, or even allowing future generations to survive catastrophic events until recovery is possible. The technology could ripple outward, reshaping not just space travel but human life itself. Cryo-sleep remains speculative, but unlike warp drives or antimatter engines, it feels tantalizingly close to the realm of real science. It doesn't ask us to break the laws of physics, only to master biology in ways that nature has already demonstrated in other species. If that frontier can be crossed, then the long sleep to another star may one day move from the pages of science fiction to the launchpads of reality. When we talk about traveling to other stars, one of the most sobering realities is the sheer amount of energy such a journey would demand. To move a spacecraft across interstellar distances isn't simply a matter of building a bigger rocket or packing more fuel. It's about confronting the fundamental physics of motion, mass, and velocity. And when you start running the numbers, the scale of the challenge becomes staggering. Let's start with something simple: getting to orbit. To launch a spacecraft from Earth into low Earth orbit requires accelerating it to around 28,000 kilometers per hour. That alone consumes enormous amounts of fuel, with modern rockets like the Falcon 9 or Saturn V burning through hundreds of tons of propellant in just minutes. Now imagine that instead of orbiting Earth, you wanted to accelerate that same mass not to orbital velocity, not even to the speed required to leave the solar system, but to a significant fraction of the speed of light, the kind of speed you'd need to realistically reach another star within a human lifetime. The difference in energy is astronomical. Energy increases with the square of velocity. That means if you double your speed, you need 4 times the energy. If you increase your speed tenfold, you need 100 times the energy. So while it takes a lot to launch a rocket to orbit, to accelerate it to even 10% the speed of light would take energy levels beyond anything humanity has ever handled. For example, let's say we want to send a relatively modest spacecraft, about the size of the James Webb Space Telescope, around 6,000 kilograms, toward Proxima Centauri at 0.1 c, 10% the speed of light. The kinetic energy required would be in the ballpark of 2.7 times 10 squared joules. To put that in perspective, that's more than the total annual energy consumption of the entire human race by a factor of thousands. And that's just for one spacecraft, not even a crewed generation ship or interstellar arc. For a larger vessel capable of carrying humans, the numbers climb even higher. A ship with a mass of 100,000 tons, a plausible minimum for something like a generation ship, accelerated to just 0.1 c would require on the order of 4.5 times 10 squared cube joules. That's equivalent to about 100 times the total energy the entire world produces in a year. And remember, that's just for acceleration. If you want to stop at your destination, you need to double that energy, once to speed up, once to slow down. Unless, of course, you're content to fly past your target star system at relativistic speed with no way to brake. This is why interstellar propulsion concepts so often sound extreme. Chemical rockets simply can't store enough energy in their fuels to come close. Nuclear propulsion gets us a step further, because nuclear reactions release orders of magnitude more energy per unit mass than chemical ones. Fusion and antimatter are even more powerful, with antimatter reactions theoretically capable of converting mass to energy with near-perfect efficiency via Einstein's famous E equals mc squared. But even if we had a reliable antimatter engine, we'd need staggering quantities of antimatter to push a human-sized ship to interstellar speeds, and producing even a single gram of antimatter today requires more energy than it yields, not to mention costs billions of dollars. Then there's the question of where we'd even get the energy. Our current civilization runs primarily on fossil fuels, solar, nuclear fission, and some hydroelectric power. The total energy consumption of Earth is around 6 times 10 squared joules per year. That's a big number, but in interstellar terms, it's modest. To launch even a single interstellar probe at high speed might require decades, even centuries, of our entire planet's energy production, unless we dramatically expand our capacity. This is where the concept of a Kardashev-scale civilization comes in, a measure of technological advancement based on energy use. Humanity today is roughly at a Type 0.7 civilization, not yet fully harnessing even the total energy of our planet. To seriously contemplate interstellar travel, many scientists argue we'd need to reach at least Type 1, fully controlling the energy output of Earth, or even Type 2, where we could harness the energy of our entire star, perhaps through a Dyson swarm of solar collectors around the Sun. Of course, energy isn't just about propulsion. A ship carrying humans for centuries would also need vast amounts to sustain life: lighting for agriculture, recycling systems, artificial gravity via rotation, medical systems, computing, and perhaps even shielding from radiation. On Earth, our biosphere receives an almost inconceivable flow of energy from the Sun every second. A self-contained starship would need to generate and recycle all of that internally. That alone would be a technological feat unlike anything we've yet achieved. Even if we could gather the required energy, there's the problem of storing and releasing it. Rocket fuel works because it stores energy in chemical bonds and releases it in a controlled way. Nuclear reactors work by controlling fission. But how do you store enough energy to push a 100,000-ton vessel to relativistic speeds? You can't simply carry that energy in tanks. The mass becomes prohibitive. This is why many interstellar propulsion concepts rely on external energy sources. Giant laser arrays on Earth or in orbit that push light sails, for example, or massive fusion reactors built directly into the ship. And then there's efficiency. Real systems are never 100% efficient. Engines waste energy as heat, radiation, or imperfect combustion. Even the most advanced propulsion system will lose some of its input energy to inefficiency, meaning the actual requirements are even higher than the raw kinetic energy equations suggest. The energy challenge of interstellar travel forces us to think not just about technology, but about civilization itself. Are we ready to build the infrastructure needed to generate and channel energies thousands or millions of times greater than our current capacities? Can we responsibly wield such power without destroying ourselves in the process? The very act of preparing for interstellar voyages might push humanity to new heights of cooperation, innovation, and sustainability. It might demand that we rethink our energy systems on a planetary scale, moving beyond fossil fuels and limited renewables toward vast solar collectors, fusion plants, or even space-based energy harvesting systems. In short, the stars are not just far away in distance, they are far away in energy terms. The gulf between where we are today and what we would need is immense, and bridging it may take not just decades, but centuries of steady progress. Yet the dream of interstellar travel ensures that we continue striving, because while the energy requirements may seem impossible, they are not infinite. They are governed by physics, and physics gives us the rules we must one day learn to master. When people imagine the dangers of interstellar travel, they often think of collisions with asteroids, system failures, or even alien encounters. But one of the most insidious and unavoidable threats out there in the void is radiation. Unlike the Earth, which is protected by both its thick atmosphere and its magnetic field, space travelers are exposed to a much harsher environment. And once you step beyond the protective bubble of the solar system, the heliosphere, the intensity of that danger rises dramatically. Radiation in deep space doesn't just make travel uncomfortable. It's a fundamental threat to human survival and to the very possibility of long-duration missions. Let's begin with the basics. Here on Earth, we are constantly bathed in a low level of cosmic radiation, but the planet's atmosphere and magnetosphere shield us from the vast majority of it. That protection disappears once you leave orbit. In low Earth orbit, like where the International Space Station resides, astronauts are already exposed to higher radiation levels, roughly 10 times higher than on Earth's surface. Even on a 6-month mission, that exposure increases their risk of cancer and can cause other physiological effects. That's within the relatively safe zone of Earth's magnetic field. Once you venture out to the Moon or Mars, that shielding is gone. And beyond the heliopause, into true interstellar space, there is nothing left to protect you at all. There are two main categories of radiation that threaten interstellar travelers: solar radiation and galactic cosmic rays. Solar radiation comes from our own star, bursts of high-energy particles during solar flares or coronal mass ejections. These can be intense, but they are at least somewhat predictable, and shielding can be designed to protect against them. Galactic cosmic rays, however, are an entirely different beast. These are high-energy particles, mostly protons and heavier nuclei, that come from outside the solar system accelerated by supernovae and other cataclysmic events across the galaxy. They travel at nearly the speed of light and carry enormous amounts of energy. When one of these particles slams into the human body, it doesn't just pass through harmlessly. It can tear through DNA, shattering strands and causing mutations. It can break molecular bonds, trigger cancer, accelerate aging, damage the nervous system, and even impair cognitive function. Unlike X-rays or gamma rays, which are primarily photons, cosmic rays often consist of heavy atomic nuclei. That makes them particularly destructive, because they don't just ionize atoms along their path, they leave a dense trail of damage that cells struggle to repair. Over years or decades of exposure, the cumulative effects could be catastrophic. And here's the catch: shielding against radiation in space is incredibly difficult. On Earth, a few feet of concrete or even water can shield us from radiation sources. But galactic cosmic rays are so energetic that they can penetrate meters of solid material. Worse, when they interact with shielding, they can sometimes create secondary radiation, new showers of particles that can be just as damaging. This means that simply piling on thicker walls doesn't always solve the problem. In fact, it can sometimes make it worse. On a practical level, this creates huge design challenges for interstellar spacecraft. A thin, lightweight craft is ideal for speed, but offers little protection. A thick, heavily shielded craft could protect its passengers, but at the cost of enormous mass. And remember, mass is the enemy when you're trying to accelerate to relativistic speeds. Some proposals suggest using water or liquid hydrogen tanks around crew compartments, since fluids can help absorb and scatter radiation more effectively. Others suggest burying habitats within the ship itself, surrounded by fuel or structural mass. One particularly creative idea is to use magnetic or electric fields as artificial shields, mimicking Earth's magnetosphere. By generating strong magnetic fields around the ship, you could, in theory, deflect charged particles before they reach the crew. But this would require enormous amounts of energy and superconducting technology that we don't yet fully control. The challenge is magnified over long durations, decades or centuries of travel, where even tiny leaks in protection would add up to devastating cumulative doses. The health risks extend far beyond cancer. Radiation exposure in space has been linked to cognitive decline, sometimes described as space brain. In animal studies, high-energy particles cause inflammation in the brain, impairing memory and learning ability. For a crew on a long voyage, this could be just as dangerous as any physical illness. If the very people responsible for operating the ship begin to lose mental sharpness, the mission could fail before it reaches its destination. Cardiovascular disease, cataracts, immune system suppression, and infertility are also associated with long-term radiation exposure. For robotic probes, radiation is less of a direct concern, but it still poses problems. Cosmic rays can flip bits in computer memory, corrupting data or even causing systems to malfunction. For a robotic interstellar probe, traveling decades or centuries through this environment, radiation hardening becomes crucial. Every circuit must be designed to withstand constant bombardment, and redundancy becomes essential. Ultimately, radiation in interstellar space is not just an obstacle, it's one of the most fundamental challenges to leaving the solar system with living beings. It forces us to rethink how we design spacecraft, how we sustain life, and how we imagine the very architecture of a mission. Unlike propulsion, which we can envision improving with new technologies, radiation protection is a stubborn, physics-based problem that may always limit what is possible. Some scientists argue that until we find radically new solutions, true interstellar human travel may remain impossible, with only robotic precursors making the journey. And yet, we're not without hope. Advances in material science, nanotechnology, and bioengineering could change the game. We may one day develop lightweight shielding materials that absorb or deflect cosmic rays more effectively. We may even enhance human biology itself, altering DNA repair mechanisms, or giving future astronauts engineered resistance to radiation damage. It may sound like science fiction, but so did spaceflight itself not long ago. The cosmic rays are relentless, pouring through interstellar space for billions of years. They do not care about our ambitions or our dreams. But if humanity is to step beyond the solar system, we must find a way to live with them, to bend them to our will, or to shield ourselves against their fury. Radiation is the invisible storm that waits for us beyond the sun's protective bubble, and solving it may be the difference between a future among the stars and a destiny forever trapped here at home. One of the most overlooked dangers of interstellar travel isn't something dramatic like a black hole, alien attack, or even the radiation storms we've just discussed. It's something far smaller, almost invisible: dust. Tiny grains of matter, micrometeoroids, floating between the stars. On Earth, dust is a nuisance, the stuff we brush off our shelves. In space, moving at interstellar speeds, dust becomes one of the deadliest obstacles imaginable. Because when you're traveling at a significant fraction of the speed of light, even a particle the size of a grain of sand can hit with the force of a bomb. Space, despite its reputation as a void, is not completely empty. It's filled with what we call the interstellar medium: gas, plasma, and dust. Dust particles range from microscopic specks, smaller than a bacterium, to larger grains, maybe a few millimeters across. Within our solar system, spacecraft already encounter dust and micrometeoroids, but because their speeds are relatively modest, tens of kilometers per second instead of thousands, the impacts usually cause only minor damage, tiny craters or scratches on surfaces. But when you accelerate to 10% the speed of light, or 30,000 kilometers per second, the rules change. Let's put this into perspective. The kinetic energy of an object increases with the square of its velocity. A micrometeoroid weighing just 1 milligram, a speck of dust, impacting at 0.1 c would release energy equivalent to several kilograms of TNT. That's like a hand grenade going off, concentrated into an impact point no bigger than a pinhead. If that dust grain strikes a spacecraft's hull, it could puncture armor, shred internal systems, and cause catastrophic depressurization. And remember, space isn't empty. There are countless such particles along any journey. Even if space between the stars is relatively clean, over light-years of travel, the odds of collisions add up to something close to certainty. For a generation ship or interstellar probe, this reality poses a nightmare for engineering. At lower speeds, spacecraft can survive micrometeoroid hits by using Whipple shields, thin layers of sacrificial material designed to vaporize incoming particles before they reach the main hull. This works fine for orbital debris around Earth or asteroid dust, but at relativistic speeds, no conventional shield is enough. The impact energy is simply too great. Imagine a bulletproof vest designed to stop a pebble, but the pebble is coming at you faster than anything you've ever seen. Some proposals for interstellar missions, such as the Breakthrough Starshot project, take this into account by sending very small, very light probes pushed by lasers to speeds of 20% the speed of light. The thinking is that the smaller the craft, the less likely it is to collide with something catastrophic. But even for tiny probes, a dust grain could mean instant destruction. This is one reason why Starshot envisions sending thousands of probes in a swarm, hoping that at least a few survive the journey. For larger ships carrying humans, redundancy like that isn't possible. You can't afford for most of your vessels to fail. You need a single ship that can withstand centuries of bombardment without being torn apart. Engineers and theorists have come up with a few ideas. One is to build enormous shielding at the front of the ship, layers of material many meters thick to absorb or deflect impacts. Another is to use plasma shields, magnetized clouds of ionized gas projected ahead of the spacecraft to vaporize incoming particles before they strike the hull. Others suggest that we could deploy swarms of small sacrificial drones, flying ahead of the main ship, taking the hits and clearing a path. Still others imagine lasers or electromagnetic fields sweeping the space in front of the ship, vaporizing dust grains before impact. But every solution comes with trade-offs. Thick shielding adds mass, and mass makes acceleration vastly harder, demanding even more energy. Plasma fields require staggering amounts of power, the kind of energy output we don't yet know how to sustain for centuries. And no matter how good the shielding, a large enough particle could still slip through. The interstellar medium may not have many of those, but all it takes is one catastrophic hit to end a mission. The risk grows as speed increases. At 0.1 c, micrometeoroids are dangerous. At 0.5 c or higher, they are apocalyptic. A single particle could release enough energy to cripple a starship entirely. This is one reason why many scientists argue that interstellar ships, if they ever carry humans, may need to travel slower than many optimistic proposals suggest. Instead of sprinting to another star at 20% of light speed, we may need to accept journeys at 1% or less, stretching missions into centuries but lowering the destructive energy of collisions to survivable levels. Of course, this then brings us back to problems like human longevity, life support, and the feasibility of generation ships. It's also worth noting that micrometeoroid impacts aren't just a danger to the hull. Sensitive equipment like telescopes, communication arrays, and radiators are particularly vulnerable. A ship crossing light years of space will need to maintain some way of radiating heat, which usually means thin, extended panels. Those panels are prime targets for dust impacts. Designing systems that can either fold away, regenerate, or be constantly replaced may be essential. This problem highlights a brutal reality: space is not our friend. The environment between stars is hostile on every level. Radiation wears down biology. Distances wear down patience. And dust, tiny, insignificant dust, could tear apart our greatest engineering marvels in the blink of an eye. When science fiction shows sleek starships cruising effortlessly through the cosmos, it skips over this terrifying truth. In reality, interstellar ships may look nothing like what we imagine. Perhaps massive, shielded fortresses, with enormous layered armor, or strange, wedge-shaped designs optimized to deflect constant impacts. Micrometeoroids force us to face the fragility of our technology. They remind us that the universe doesn't scale its dangers to our ambitions. The stars are waiting, but between us and them lies a minefield of invisible bullets, flying endlessly through the dark. If we are to cross safely, we must invent ways to protect ourselves from the smallest threats, because at near-light speed, those smallest threats become the deadliest of all. When we talk about sending humans beyond the solar system, we're not just talking about a long road trip. We're talking about journeys that last centuries, maybe even millennia. That introduces one of the most daunting challenges of all: human longevity. How do you keep people alive, healthy, and functional in an environment that is utterly hostile, for timescales that stretch far beyond a single human lifespan? The truth is, this question might be even more difficult than building engines powerful enough to propel us to the stars. Propulsion is about physics and engineering, but longevity is about biology, psychology, and the deep limits of human survival. Let's start with the obvious. The average human lifespan today is somewhere between 70 and 85 years, depending on where you live. Even if medical advances continue, pushing lifespans past 100, that still falls dramatically short of the centuries required for interstellar travel. At best, a single crew could survive a trip to the nearest stars if the voyage lasted only a few decades. But that's impossible with current or near-term propulsion technologies. At speeds even remotely achievable, travel to Proxima Centauri would take thousands of years. No single person could endure that. This leads to a few possibilities. One is the idea of the generation ship, which we touched on earlier. Instead of trying to extend individual human life, you design a spacecraft where families live, work, and have children, generation after generation. Each new generation inherits the mission, until finally, centuries later, descendants of the original crew arrive at their destination. On paper, it's elegant. In practice, it's enormously complicated. Human societies are unpredictable. Over hundreds of years, cultural drift could reshape the crew's values, possibly making them forget the mission entirely. They could split into factions, rebel against the leadership, or simply decide they no longer want to arrive at a destination chosen centuries before their birth. The problem of longevity in this case isn't biological, it's cultural survival across vast timescales. But let's assume for a moment that we don't want to rely on passing the mission from generation to generation. Then we face the direct problem of radically extending individual lifespans. Can humans be kept alive for hundreds of years? Science is just beginning to scratch the surface of longevity research. We know that aging is driven by processes like DNA damage, cellular senescence, and the shortening of telomeres. Experiments on animals show promise that some of these processes can be slowed or reversed. Technologies like CRISPR and research into stem cells all suggest that we might one day delay aging. There's even speculation about biological immortality, not that humans could never die, but that the process of aging itself could be halted, leaving accidents and disease as the main risks. If that dream were realized, then interstellar travel could, in theory, be endured by a single generation of ageless travelers. But longevity isn't just about years on a calendar. In space, the environment itself accelerates aging. Radiation damages DNA, speeds up cell decay, and increases cancer risk. Microgravity erodes muscles and bones, leading to osteoporosis-like conditions within months. Fluids redistribute, vision deteriorates, and immune systems weaken. Even if we cracked the genetic code of aging, surviving in deep space would require constant medical intervention to counteract these effects. We would need artificial gravity, perhaps through rotating habitats, to preserve musculoskeletal health. We would need advanced shielding, medical nanotechnology, or even genetic engineering to protect against radiation. And we'd need new methods of maintaining mental and emotional well-being in the face of extreme isolation. Because that's the other side of longevity, the psychological challenge. Imagine living your entire life inside a metal habitat, never feeling fresh air, never walking on grass, never seeing a horizon. For the first few years, maybe even decades, humans could adapt. But what about century after century? How would the human mind cope with the monotony, the confinement, and the knowledge that you may never reach the destination within your lifetime? Depression, anxiety, and social conflict would become just as threatening as radiation or mechanical failure. Longevity isn't just about keeping the body alive, it's about keeping the mind and spirit resilient across unimaginable stretches of time. There are a few science fiction-inspired alternatives. Cryogenic sleep or suspended animation is one. Instead of extending life, you put travelers into a deep hibernation state, where biological processes slow to a crawl. If perfected, this could allow crews to survive centuries without experiencing them, essentially skipping the long wait. But as we discussed earlier, cryosleep remains speculative. It's been achieved in small animals like frogs and insects, but not in mammals at the scale required. The technology may one day exist, but right now, it's more of a dream than a plan. Another approach could be mind uploading, transferring human consciousness into machines. If a human mind could be digitized, stored, and run on robust hardware, then longevity becomes a matter of keeping circuits functioning, not flesh. Machines can last far longer than organic bodies, especially if designed with redundancy and self-repair. But this raises profound philosophical questions. Would a digital copy truly be you, or just a simulation? And would humanity be satisfied sending digital proxies to the stars? Or does the dream require flesh and blood explorers? Even without radical life extension breakthroughs, it's possible to imagine hybrid solutions. For example, a combination of generation ships and biomedical advances could mean crews live far longer than we do today, say 150 or 200 years, while also relying on descendants to complete the mission. Advances in AI might reduce the workload, making survival less taxing. Robotics could maintain the ship, while humans focus on preserving their community. In this sense, the longevity challenge could be shared between biology and technology. But no matter which path is chosen, human longevity remains a central bottleneck for interstellar travel. It's a reminder that we're not built for the cosmos. Our bodies evolved for Earth, its air, its gravity, its rhythms of day and night. To take those fragile bodies beyond the solar system, into the dark gulfs between stars, is to fight against everything nature has made us to be. We may one day master propulsion, solve the problem of radiation, and build starships capable of crossing light years. But unless we can keep human beings alive, truly alive, body and soul, for centuries, those ships may fly empty, carrying only machines. The question of whether humans will ever leave the solar system inevitably runs into one of the most sobering and practical realities: cost. Dreams of interstellar exploration often soar into the realms of physics, biology, and science fiction. But when you bring those dreams down to Earth, they smash into economics. It's not just a matter of building an engine that can reach near-light speeds or constructing a generation ship that can sustain life for centuries. It's about whether humanity can muster the money, the materials, the energy, and the willpower to actually attempt it. And when we run the numbers, the sheer scale of the resources required makes even our grandest projects today, things like the International Space Station or the Apollo program, look like pocket change. Let's begin by looking at context. The Apollo program, which landed humans on the moon in the 1960s and 70s, cost about $25 billion at the time, around $150 billion in today's dollars. That was for missions only a few days long, covering a distance of about 384,000 kilometers. The International Space Station, humanity's most expensive single project to date, has cost over $150 billion and represents decades of international cooperation, all to maintain a permanent crew of fewer than 10 people in low Earth orbit, only a few hundred kilometers above the surface. By comparison, interstellar travel requires building spacecraft millions of times more complex, far larger, and capable of surviving journeys not of days or years, but centuries. The first big cost category would be propulsion energy. To accelerate a spacecraft with mass comparable to even a small city to a fraction of light speed would demand energy on the order of what entire nations consume in years. Let's put it bluntly, to push a 1,000-ton ship, which is tiny compared to what we'd likely need, to 10% the speed of light requires about 4.5 times 10 to the power of 21 joules of energy. That's more than all the electricity generated on Earth in an entire year by a factor of tens of thousands. To generate that kind of power, we'd need to harness fusion reactors, antimatter production, or entire solar farms spanning kilometers in orbit. Even then, the cost of building and operating such systems would reach into the quadrillions of dollars, numbers that dwarf the global economy as it exists today. Then there's the cost of the ship itself. A generation ship or even a large robotic interstellar probe would require not just a rocket, but a self-contained world. It would need shielding many meters thick to survive radiation and micrometeoroid impacts, closed-loop life support systems capable of recycling air, water, and nutrients indefinitely, agricultural modules to grow food, medical facilities, power plants, manufacturing capabilities for repairs, and redundancies upon redundancies to ensure survival over hundreds of years. That's not a spacecraft, it's more like building a city in space, or even a mobile colony. Constructing such a vessel would likely require mining asteroids for metals, processing enormous quantities of raw material in orbit, and coordinating global industries for decades. The price tag? Easily trillions, possibly tens or hundreds of trillions of dollars. Now add in human factors. A crewed mission would require training, genetic diversity for a population capable of sustaining itself, and psychological support systems. The cost of maintaining such a crew in deep space isn't just technical, it's cultural. You'd be investing in education, governance models, and even entertainment infrastructures for a society that has to exist completely cut off from Earth. That's not something you buy once, it's a permanent expense. All of this raises the question, who pays? No single nation could realistically fund such an endeavor alone. The entire world's annual GDP is roughly $100 trillion. An interstellar project could easily require a sustained commitment of 1 to 10% of global GDP over centuries. That implies nothing short of a unified planetary effort, a collaboration larger than anything humanity has ever attempted. But beyond raw money, there are resource costs. Every ton of material sent into space requires energy to lift it out of Earth's gravity well. Right now, launching 1 kilogram into orbit costs thousands of dollars. SpaceX and other companies are bringing that cost down with reusable rockets, but even if launch costs drop to tens of dollars per kilogram, lifting the millions of tons required for a Starship is still a colossal challenge. Some argue that instead of launching everything from Earth, we'll need to mine and manufacture directly in space. That means building massive orbital factories, developing asteroid mining on an industrial scale, and perhaps even setting up entire infrastructure networks beyond Earth before we can seriously think about interstellar ships. The resources required aren't just financial, they're planetary in scope. Yet, cost doesn't just measure in dollars and steel, it measures in opportunity costs. If humanity spends trillions on a Starship, what doesn't get funded back home? Climate change solutions? Poverty eradication? Healthcare? Even if the dream of leaving the solar system feels noble, the sacrifices required might be too much for societies struggling with immediate, earthbound crises. This is perhaps the most sobering challenge, convincing billions of people that investing in a future centuries away is worth their sacrifices today. But here's the counterpoint. The history of humanity shows that when survival or exploration demands it, resources are found. The Great Pyramids of Egypt, the cathedrals of Europe, the Apollo program, all of these were colossal expenditures of time and treasure, often with little immediate practical payoff, but they left legacies that lasted for centuries or inspired generations. If Earth ever faces existential threats, whether from climate collapse, asteroid impact, or the slow death of the Sun, suddenly, the cost of interstellar travel might look less like an extravagance and more like an insurance policy for the species. Ultimately, the cost and resources required to send humans beyond the solar system are staggering, beyond anything we've yet attempted. It would take not just money, but the redirection of entire economies, the invention of new industries in space, and a level of international cooperation that feels almost utopian. And yet, when weighed against the survival of humanity, the price might one day feel not only worth it, but unavoidable. The cost of staying confined to one solar system forever could ultimately be higher than the cost of venturing into the stars. When we frame the idea of leaving the solar system not as a science fiction dream but as a survival strategy, the conversation takes on a very different weight. Suddenly, it isn't just about curiosity or adventure. It becomes about the long-term survival of the human race. Earth has been our home for hundreds of thousands of years, and it has nurtured every civilization, every culture, every life that has ever existed. But as permanent as it feels, Earth is not invincible, and it is not eternal. If humanity intends to survive not just for centuries but for millions of years, then leaving the solar system might not just be an option, it could be a necessity. The threats to humanity's survival on Earth come in many forms. Some are natural, some are self-inflicted, and some are guaranteed by the laws of astrophysics. Let's start with the natural threats. Asteroids and comets have struck Earth in the past, causing mass extinctions. The most famous example is the asteroid that struck 66 million years ago, wiping out the dinosaurs and reshaping the planet's ecosystems. Smaller impacts have occurred more recently, such as the Tunguska event in 1908 or the Chelyabinsk meteor in 2013, reminding us that Earth is not shielded from cosmic hazards. A single large asteroid strike could devastate global civilization or even render Earth uninhabitable for humans. Then there are threats from space we cannot control: gamma-ray bursts, supernovae, or even the long-term brightening of the Sun. Over the next billion years, the Sun will gradually heat up, boiling Earth's oceans and making the planet uninhabitable long before the Sun becomes a red giant. Even if humanity solves every short-term problem, Earth has an expiration date written into the laws of stellar evolution. Staying here forever is simply not an option. But perhaps the more immediate threats are the ones we create ourselves. Climate change, nuclear war, pandemics, and runaway artificial intelligence all pose existential risks. A warming planet could destabilize ecosystems and economies, making survival difficult. Nuclear conflict could bring about a nuclear winter that devastates food supplies and collapses civilizations. Pandemics could wipe out large populations. And as we create ever more powerful technologies, we also create new ways to destroy ourselves. When seen from this angle, leaving the solar system starts to look less like a fantasy and more like a long-term insurance policy. Just as investors diversify their portfolios to reduce risk, humanity might need to diversify its locations in the cosmos. If all of us remain on one planet, or even within one solar system, then a single disaster could end us. But if humans, or at least human descendants or artificial intelligences carrying our legacy, spread to other star systems, then no single catastrophe could wipe us out completely. Survival becomes about redundancy. This isn't just a practical idea, it's a philosophical one. Carl Sagan once said that staying on Earth forever would be like never leaving the cradle. If we remain confined here, no matter how advanced we become, we remain vulnerable. But if we spread outward, if we carry the light of human civilization to other stars, then we ensure that our story does not end with one bad roll of the cosmic dice. Leaving the solar system becomes the ultimate act of species preservation. Of course, survival in interstellar space is not guaranteed. The challenges we've discussed, radiation, micrometeoroids, longevity, and cost, are monumental. But humanity has always thrived under pressure. The same ingenuity that carried us from caves to cities, from canoes to rockets, could one day carry us from star to star. The key difference is that the stakes are much higher now. Exploration isn't just about curiosity anymore. It's about existence. Even if leaving the solar system takes thousands of years, every step toward that goal increases humanity's odds of survival. Colonizing Mars or building permanent habitats in orbit teaches us how to live beyond Earth. Mining asteroids or harvesting solar energy on a massive scale gives us the tools for self-sufficiency in space. Creating fusion power or advanced propulsion systems gives us the ability to move outward. Each milestone along the way builds resilience, and resilience is survival. It's also worth noting that survival doesn't necessarily mean biological survival in the way we imagine today. It might not be flesh and blood humans who cross interstellar space, but genetically engineered descendants, or human-AI hybrids, or even uploaded minds inside machines. The form may change, but the continuity of culture, memory, and knowledge could remain. From the perspective of survival, what matters is that something of humanity carries on. And here's the paradox. Leaving the solar system as a survival strategy may seem impossibly difficult now, but the alternative, remaining bound to one fragile planet orbiting one star, is infinitely riskier in the long run. The Earth is a beautiful, miraculous world, but it is not permanent. The solar system itself will one day become inhospitable. To survive, we must eventually become more than a planetary or even solar species. We must become interstellar. This is not a plan for the next century, or even the next millennium. It is a vision for the deep future of humanity. And perhaps that's what makes it so powerful. Survival gives purpose to the struggle. It frames the immense cost, the scientific hurdles, and the decades, or centuries, of effort not as luxuries or fantasies, but as investments in the most important project humanity could ever undertake, ensuring that we endure. If survival is the rational argument for leaving the solar system, then exploration is the emotional one. Beyond the practical need to ensure our species continues, there is a deeply ingrained part of human nature that drives us to venture outward, to push past boundaries, and to see what lies beyond the horizon. This urge is as old as humanity itself. It has guided our migrations across continents, our voyages across oceans, and our leaps into the skies and into space. The exploration drive is one of the most powerful forces in our history, and it may be the very thing that carries us to the stars. Think about how many times in human history we have encountered a boundary that seemed absolute. Tens of thousands of years ago, early humans walked out of Africa into unknown lands. For them, every step into unfamiliar territory was a gamble. New predators, new climates, new challenges. But curiosity and necessity kept them moving forward until humanity spread across nearly every habitable corner of the globe. Thousands of years later, when vast oceans seemed impassable, civilizations developed ships that carried them to distant continents. These journeys were dangerous, often fatal, yet they reshaped human history. When the sky itself was thought to be the ultimate ceiling, people dreamed of flight, and eventually built machines that soared above the Earth. Space is simply the next frontier. The moon landings of the 20th century weren't just scientific missions, they were symbolic acts of exploration. Neil Armstrong's famous words resonated so deeply not just because humanity had survived a technical challenge, but because he expressed something primal. We had stepped beyond our world into a place no human had ever been. That spirit of exploration taps into something universal. We want to know. We want to see. We want to experience. The drive to explore isn't just about geography, it's about identity. Humans are storytellers, and our stories are filled with journeys. From Odysseus's voyage home in Greek myth to the Polynesian navigators crossing the Pacific to the science fiction epics of today, exploration defines our cultural imagination. The idea of venturing into the unknown resonates because it mirrors the human condition itself. Life is a journey into mystery, and the cosmos is the ultimate unknown. When we think about leaving the solar system, some may argue that the scale is too vast, the risks too great, the costs too high. But history shows us that humans rarely stop at obstacles. The impossible of one era becomes the inevitable of the next. Sailing around the Earth was once unthinkable. Flying through the skies was once a fantasy. Walking on the moon was once pure science fiction. Each time, people said we can't, until we did. The same may one day be true for traveling to other stars. Exploration is not always rational in the short term. Many great voyages in history yielded little immediate payoff. The first explorers who crossed oceans often returned with little more than stories and hardship. But their journeys opened the way for generations that followed. The same is true in space. Sending probes to Mars or beyond doesn't give us instant riches. it gives us knowledge, experience, and inspiration. That may not seem tangible, but it builds the foundation for greater achievements later. Exploration is a long game, and humanity has always played it, often without realizing it. It's also worth noting that exploration is rarely about utility alone. It's about wonder. When we gaze at the stars on a clear night, there's a universal feeling of awe that transcends culture and time. Children dream of being astronauts not because they want to solve energy crises or build orbital economies, but because they feel the pull of the unknown. That awe, that wonder, is fuel. It motivates people to study science, to invent, to build. The drive to explore may be intangible, but it has concrete effects. It moves societies forward. At the same time, the exploration drive is double-edged. Human history is filled with conquests and colonization that came with tragedy as well as triumph. Venturing into new frontiers often meant clashing with those who already lived there. When we look at interstellar exploration, the stakes change. We don't yet know if there are others to encounter, or what responsibilities we'll carry into those encounters. But even acknowledging those ethical questions, the drive itself remains undeniable. We explore because we can, and because something within us demands it. Leaving the solar system might ultimately be an act of necessity for survival, but it will also be an act of choice born from curiosity. Even if Earth were guaranteed safe forever, even if there were no asteroid threats or solar evolution to fear, humanity would likely still dream of the stars. The desire to explore doesn't fade when safety is assured, it intensifies. It is what carried us from forests to plains, from huts to cities, from continents to the heavens. We are explorers by nature, and the solar system is not a cage, it is a stepping stone. The moment we cross into interstellar space with intent, not just with robotic probes but with missions designed to seek, to discover, and to learn, humanity will once again be honoring its oldest instinct, to go where we have never gone before. And in that sense, leaving the solar system is not just about technology or survival, it's about fulfilling something fundamental in who we are. If exploration is about curiosity and survival is about necessity, then the search for life beyond our solar system combines both. Few questions ignite the imagination like this one. Are we alone in the universe? The stars are not just distant lights. Many of them are suns with their own planetary systems, some of which may harbor worlds where life has taken root. Leaving our solar system might ultimately be driven as much by this search as by anything else, because discovering another inhabited world, or even a habitable but empty one, would be one of the most profound moments in human history. For centuries, people have wondered whether other worlds might hold life. Ancient philosophers speculated about countless other Earths orbiting distant stars. In the modern era, this speculation has become a scientific pursuit. Astronomers using telescopes on Earth and in orbit have now confirmed thousands of exoplanets, planets outside our solar system. These discoveries reveal that planets are not rare but common. Nearly every star we study appears to have planets, and some of them orbit in regions where liquid water could exist, the so-called habitable zone. The implication is staggering. The galaxy may be teeming with worlds that could, under the right conditions, support life. One of the closest and most intriguing candidates lies in the very star system nearest to us, Proxima Centauri. Around this faint red dwarf star, astronomers have detected a planet known as Proxima b. It orbits within the star's habitable zone, meaning temperatures could, in theory, allow liquid water on its surface. Proxima b is not a perfect twin of Earth. Its star is more volatile, and its environment may be harsh, but its mere existence hints at possibilities. If the nearest star has a potentially habitable planet, how many more might lie scattered across the Milky Way? The search for life is not just about finding another Earth. Even discovering microbial life elsewhere would revolutionize science. If life can emerge independently in two different places within the same galaxy, then it is probably widespread across the cosmos. On the other hand, if life proves extraordinarily rare, then Earth may be far more unique than we ever imagined. Either result would reshape our understanding of biology, evolution, and our place in the universe. But to truly know, we will need to look closely at exoplanets, and that may require going there. Leaving the solar system to search for life would not be easy, but it might be one of the most powerful motivators humanity has. Imagine the implications of discovering not just microbial organisms but complex ecosystems, or even intelligent civilizations. Such a discovery would alter philosophy, science, and human identity in ways we can hardly predict. The thought that other beings, perhaps far older or more advanced than us, may look up at their own night skies and wonder if they are alone, it's almost irresistible. The quest to answer that question pulls us forward. Even if alien life remains elusive, the search for habitable worlds is equally vital. Earth is the only known planet where life thrives, but it may not always remain so. Climate, geology, and stellar evolution all change over time. If humanity wants to endure, we may eventually need to find other worlds where life can take hold. The exoplanets we've already discovered suggest that there may be millions of rocky, Earth-like planets in the galaxy. Some might be deserts, some frozen, some storm-racked, but perhaps a few are welcoming. Finding them may be essential to our survival. Technology is slowly bringing these possibilities into focus. Telescopes like the James Webb Space Telescope and its successors are beginning to analyze the atmospheres of exoplanets, searching for signs of water, oxygen, methane, and other indicators of habitability or even biological activity. But remote sensing has limits. At some point, to truly know, we will need to send probes, and eventually people, beyond our solar system to see for ourselves. That dream may be centuries away, but it grows closer with each discovery. The search for life is also deeply human. It connects to our myths, our hopes, and our fears. Some dream of finding kindred civilizations, beings who can teach us, warn us, or simply prove that we are not alone. Others fear what might be out there, pointing to the possibility that first contact could be dangerous. Either way, the curiosity persists. The stars beckon us not just as destinations, but as questions. Every exoplanet discovered whispers, could I host life? Could I be a home? Leaving the solar system may ultimately be framed not only as a scientific mission but as a profoundly existential one. To know whether life exists elsewhere is to know whether humanity is a cosmic accident or part of a larger story of biology written across the galaxy. That question alone could propel us across interstellar distances, fueling the effort needed to make the impossible possible. When we think about the practical first steps toward leaving the solar system, interstellar probes stand out as the most realistic path forward. Unlike the enormous, crude generation ships or the exotic warp drives of science fiction, probes represent a near-term, tangible way of extending humanity's reach into interstellar space. They allow us to explore beyond the heliopause without risking human lives and without needing the astronomical resources required to sustain people on such epic journeys. And among the most ambitious concepts currently on the drawing board is Breakthrough Starshot, a project that may, within this century, send the first human-made craft to another star system. The idea behind Breakthrough Starshot is breathtaking in its simplicity yet audacious in its ambition. Instead of building a massive rocket that tries to carry its own fuel across light-years of space, the plan is to build incredibly small, lightweight probes, essentially tiny spacecraft weighing only a few grams, and propel them to a significant fraction of the speed of light using powerful ground-based lasers. These nanocraft, as they are called, would be attached to ultra-thin, reflective light sails. When an array of lasers on Earth fires, it would push the sail with photons, accelerating the probe to speeds unimaginable for conventional spacecraft. The target is around 20% of the speed of light, or roughly 60,000 kilometers per second. At that speed, a probe could reach Proxima Centauri, the nearest star system, in just over 20 years. Compare that to the 70,000 plus years it would take Voyager to make the same trip at its current pace, and you see the revolutionary leap this represents. The probes themselves would be small but powerful. Each would carry cameras, communication equipment, navigation systems, and scientific instruments, all miniaturized to fit within a few grams of mass. As they zip past exoplanets like Proxima b, they could snap images, measure atmospheric composition, and relay data back to Earth. Even a single photograph of an alien world orbiting another star, taken by a probe we built, would be a historic achievement, a moment that changes human perspective forever. Of course, the challenges are immense. The lasers required to push these sails would need to be among the most powerful ever constructed, with a system capable of generating gigawatts of energy. Keeping the beam steady over thousands of kilometers of atmosphere, without dispersing or damaging the sails, is another enormous hurdle. Then there's the problem of communication. How do you send a signal back across 4 light-years of space from a probe the size of a microchip with only a tiny power supply? Solutions involve using focused laser transmitters on the probes, but aligning them with Earth across such vast distances is an engineering challenge of staggering proportions. And yet, the fact that scientists are seriously considering these problems is significant. Breakthrough Starshot, launched by Yuri Milner with support from Stephen Hawking and other visionaries, isn't science fiction, it's a funded research initiative. While it may take decades to develop the necessary technology, the concept itself is grounded in physics we already understand. Photons can exert pressure, sails can capture that momentum, and lasers can provide the energy. The difficulties are technological, not theoretical, and history shows that technological barriers tend to fall given enough time and effort. What's also compelling is the scalability of the idea. Thousands of probes could be launched at once, like a swarm of interstellar scouts. Most might fail, be destroyed by collisions with interstellar dust, or lose communication, but even if a handful survive and transmit back, the mission would be successful. In this way, the redundancy mimics nature's own approach to exploration, where many seeds are cast into the wind, but only a few take root. Breakthrough Starshot is not the only interstellar probe concept. Variations include nuclear-powered microprobes, advanced ion drive craft, or larger sails pushed not by Earth-based lasers but by sunlight itself. Each shares the same advantage. They avoid the impossible energy demands of pushing a massive crewed ship across light-years and instead focus on small, agile, unmanned explorers. These robotic pioneers could pave the way for future generations of human missions by mapping nearby star systems, identifying habitable planets, and even flagging potential hazards. When humanity finally does leave the solar system in a meaningful way, it is almost certain that robots will lead the charge. Just as robotic explorers like Voyager, Cassini, and New Horizons have prepared the way for our understanding of the solar system, interstellar probes will prepare the way for our journeys to the stars. They will be our scouts, our eyes and ears in distant places we cannot yet reach ourselves. In this sense, Breakthrough Starshot and similar projects are not just technical endeavors, they are symbolic. They embody a willingness to try, to stretch, to look beyond. They tell us that leaving the solar system is not merely a dream for the far future but something we are already taking steps toward, right now, in the early 21st century. If interstellar probes like Breakthrough Starshot represent the first flickers of humanity reaching beyond our solar system, then robotic precursors are the natural next step. Long before human beings ever strap themselves into a vessel bound for the stars, machines will pave the way. This is not just a matter of practicality, it is an inevitability. Robots don't need air to breathe, food to eat, or water to drink. They don't age, they don't suffer from radiation sickness, and they don't need protection from the crushing psychological burden of infinite blackness. That makes them the ideal pioneers for interstellar exploration, the scouts that will venture into the void where no human has yet dared. Looking back at our history of exploration in space, the pattern is clear. Robots have always gone first. Before Neil Armstrong and Buzz Aldrin ever set foot on the moon, unmanned probes like Luna 2 and Surveyor tested the terrain and landing techniques. Before humans even consider traveling to Mars, we've already sent orbiters, landers, and rovers. Machines like Spirit, Opportunity, Curiosity, and Perseverance, to map, analyze, and prepare. The same logic extends outward. If we dare to leave the solar system, it will be robots that blaze the trail. The advantages are overwhelming. For one, the timescales involved in interstellar travel make crewed missions almost unthinkable with our current capabilities. Even the most optimistic propulsion concepts still take decades, if not centuries, to cross interstellar distances. A human crew would need life support systems, food supplies, artificial gravity, shielding from radiation, and protection against micrometeoroids for the entire duration of the journey. Robots, on the other hand, can be hardened against radiation, designed to hibernate for centuries if necessary, and reawaken to perform their tasks. They don't mind waiting. Another key factor is cost. Building a generation ship or cryosleep vessel large enough to carry humans would require resources on a scale far beyond anything humanity has ever attempted. Robotic precursors, in contrast, can be made much smaller, lighter, and cheaper. A swarm of robotic probes could be launched with relative efficiency, allowing for redundancy. If some fail, others may succeed. This approach mirrors biological evolution, where success doesn't hinge on a single organism but on the collective adaptability of many attempts. Future robotic precursors may not look like the machines we're familiar with today. As artificial intelligence continues to advance, the line between probe and crew may blur. Imagine an interstellar robot equipped not only with scientific instruments but with an AI capable of independent decision-making, able to adapt to unforeseen challenges, navigate complex star systems, and even design its own repairs using local resources. Such machines could serve as both explorers and settlers, seeding distant systems with the technology needed for eventual human arrival. One particularly exciting concept is the use of self-replicating robots, sometimes called von Neumann probes. In theory, a single robotic precursor equipped with advanced manufacturing capabilities could land on a suitable asteroid or planet in another system, harvest raw materials, and build copies of itself. Those copies could then spread further, multiplying the exploration effort exponentially. While this remains purely speculative and fraught with ethical questions, it demonstrates the potential power of robotic precursors to carry humanity's reach far faster and farther than we could ever manage with human-only missions. We should also consider the psychological and philosophical value of robotic precursors. Even if we can't yet travel to another star ourselves, knowing that a machine built by human hands is out there, crossing the interstellar void, carrying our questions into the unknown, can be profoundly meaningful. Just as Voyager's golden record carries music, greetings, and images from Earth into the cosmic night, future robotic precursors could carry not just instruments but messages of who we are, serving as ambassadors for humanity long before we ever arrive in person. What's more, robotic missions will allow us to answer crucial questions before risking human lives. Is a particular exoplanet habitable? Does it have dangerous conditions we cannot anticipate from afar? Are there traces of life, microbial or otherwise, that demand careful handling? Robots can scout, sample, and transmit back vital data, giving us the information we need to prepare for eventual colonization or contact. In this way, robotic precursors serve not only as pathfinders but as protectors. They minimize the risks, gather intelligence, and buy us time to develop the technologies we'll need for human journeys. They are the vanguard of our species' interstellar ambitions, the first footsteps, albeit mechanical ones, into the great unknown. And perhaps most importantly, robotic precursors will help us answer the most profound question of all. Is the universe empty or alive? They will likely be the first to peer into alien skies, to skim past the oceans or deserts of distant exoplanets, to test their atmospheres and scan for biosignatures. If life is out there, it may be robots, not humans, that discover it first. If humanity ever dreams of leaving the solar system in crewed ships, one of the first lessons we must learn is how to live in space permanently, not as temporary visitors. Right now, the International Space Station proves we can sustain a handful of astronauts in orbit for months at a time, but that is a fragile arrangement requiring constant resupply from Earth. For interstellar journeys, where resupply is impossible, we'll need a completely different approach. Building self-sufficient habitats capable of housing not just crews, but entire societies. This is where the visionary concepts of large-scale space habitats come into play, with O'Neill cylinders standing out as some of the most compelling models. Proposed by physicist Gerard K. O'Neill in the 1970s, O'Neill cylinders are massive rotating habitats, essentially giant cylinders miles long and several miles wide, spinning to simulate gravity through centrifugal force. Inside such a structure, you could build farmland, cities, rivers, and forests, an entire Earth-like environment, enclosed within a metal shell drifting through space. Sunlight could be redirected into the habitat by massive mirrors, creating day and night cycles. In theory, these cylinders could support tens of thousands or even millions of people, functioning like miniature worlds floating in the void. Why does this matter for interstellar travel? Because interstellar journeys aren't weekend trips, they span decades, centuries, or longer. A ship carrying humans to another star cannot just be a cramped capsule. It must become a world in itself, a living, breathing environment where people can work, grow food, raise families, and pass on knowledge. O'Neill cylinders offer a vision of how we might achieve that: self-contained, self-sustaining habitats where generations could live comfortably while crossing the light years. Other space habitat concepts have been proposed as well, such as Stanford Torrey, donut-shaped habitats that also use rotation to simulate gravity, or Banal spheres, which are spherical structures with habitable interiors. Each shares the same fundamental idea, creating a stable, long-term home for humans away from Earth's surface. In a sense, they represent a rehearsal for interstellar journeys. If we can't sustain 1 million people in an orbiting habitat around Earth or in the asteroid belt, how can we expect to sustain them on a voyage lasting centuries across the gulf between stars? Building such habitats also teaches us crucial lessons about closed-loop life support systems. On Earth, the biosphere naturally recycles water, air, and nutrients. In space, we'll need artificial systems that do the same, capturing carbon dioxide and turning it back into oxygen, purifying water endlessly, recycling waste into usable resources. These technologies are in their infancy today, tested on small scales aboard the ISS, but in a large-scale habitat, they would need to function flawlessly for centuries. Perfecting that balance in orbit around Earth or within the solar system is a necessary precursor to attempting it in interstellar space. There's also the matter of culture and psychology. Interstellar journeys are not just about surviving, they are about living. For a crew trapped in a metal box for generations, monotony, isolation, and despair could be as deadly as any technical failure. Large habitats like O'Neill cylinders address this by creating environments where nature, diversity, and space for social interaction can flourish. Imagine walking along a riverbank inside a rotating cylinder, seeing fields stretching toward a sky that curves upward, filled not with stars but with farmland inverted above your head. This surreal yet familiar environment could help preserve sanity and culture across long voyages. Moreover, building space habitats prepares us for the challenges of independence. Unlike colonies on Mars or the Moon, which might still maintain supply links to Earth, a spacefaring habitat has to be completely self-reliant. It has to mine asteroids for raw materials, harvest solar energy for power, and grow all its own food. In doing so, humanity would be forced to become a truly space-dwelling civilization, no longer tied to the surface of a single planet. This transition, from planetary to space-based civilization, is arguably the necessary first step before we can ever dream of becoming interstellar. Even if we never build O'Neill cylinders for the purpose of star travel, their construction within our solar system could change everything. Imagine vast cities orbiting near Earth, manufacturing goods from asteroid materials, farming in endless artificial valleys, and housing populations larger than Earth's. Such habitats could act as staging grounds for interstellar missions, shipyards in orbit, producing the great generation ships or fusion vessels that would one day push beyond the heliopause. The importance of building habitats like these cannot be overstated. They represent practice for the future, training wheels for interstellar ambitions. By learning how to build worlds of our own in space, we gradually loosen our dependence on Earth and learn the art of creating ecosystems from scratch. Once we master that, then whether the journey is across the solar system or across the stars, we'll carry the ability to make any corner of the universe our home. Before we can even dream of launching a crewed starship or building a generation vessel, humanity faces a daunting list of technologies that must first be mastered. The sheer scale of interstellar travel forces us to rethink everything we know about propulsion, energy, sustainability, and intelligence. Right now, our spacecraft are essentially fragile tin cans compared to what's needed for the stars. To cross interstellar space, we'll need breakthroughs in multiple fields simultaneously, and it's not an exaggeration to say that without these stepping stones, the dream of leaving the solar system will remain nothing more than fantasy. One of the most critical technologies is propulsion beyond chemical rockets. Fusion power is at the heart of this challenge. The energy locked within atomic nuclei is millions of times greater than that of chemical reactions, making fusion one of the only realistic methods to propel ships at a fraction of light speed. Projects like Daedalus and Icarus, which we touched on earlier, were only blueprints, but they pointed in the right direction. A ship driven by controlled nuclear fusion could, at least in theory, accelerate to 10% or more of the speed of light. If such technology ever moves from theoretical design to practical engineering, it would slash travel times to the nearest stars from tens of thousands of years to a few centuries. Still monumental, but within the scope of civilization rather than geological time. But propulsion is only half the battle. We also need artificial intelligence advanced enough to manage and sustain such missions. Think about what an interstellar probe, or worse, a crewed ship, would face in deep space. Communication delays with Earth could span years, making remote control impossible. That means AI must operate independently, diagnosing problems, repairing systems, and even making judgment calls about navigation, science goals, or emergencies without waiting for human instructions. A robotic precursor probe might require a narrow AI capable of engineering-level problem-solving, but a crewed vessel would need something far more sophisticated, able to manage entire biospheres, maintain mental health for passengers, and adapt to unpredictable crises. In a way, the AI on board would become not just a tool but a co-pilot, a guardian, and possibly even a partner civilization accompanying humanity into the void. Fusion and AI, though, are only the beginning. Another stepping stone is energy. Interstellar travel demands unimaginable amounts of it, not just for propulsion but for maintaining life over centuries. Current spacecraft rely on solar power, but solar panels become useless as you move far from the sun. Beyond Pluto, sunlight is too faint to power much of anything. This means interstellar craft will need nuclear power, fusion reactors, or perhaps even entirely new energy sources we haven't yet discovered. We'll need compact, long-lasting systems that can run without refueling for decades or centuries, a challenge we've never yet solved on such scales. Then there's the question of materials. A starship has to endure environments far harsher than Earth orbit. It must withstand cosmic rays, micrometeoroid impacts at near-relativistic speeds, and centuries of wear without resupply. This calls for materials far stronger and more resilient than anything commonly available today. Advances in nanotechnology, self-healing materials, and ultra-strong composites may prove essential. Imagine hulls that can repair microscopic damage automatically, or shielding that regenerates after bombardment. Without innovations like these, the ship itself could fail long before reaching its destination. Biotechnology is another stepping stone. If humans are going to live aboard these vessels for generations, or survive in cryo-sleep, we'll need mastery over our biology. That includes protection against radiation damage, methods to slow or halt aging, and ways to maintain psychological health in confined environments. Genetic engineering may even play a role, preparing humans for life in deep space by enhancing our resilience. At the very least, we will need closed-loop life support systems that can recycle air, water, and nutrients with near-perfect efficiency. A feat biology does effortlessly on Earth but which we must painstakingly recreate artificially. And finally, perhaps the most subtle but vital stepping stone, the culture of cooperation and sustained commitment. Interstellar projects cannot be built in a decade or even a century by one nation. They demand long-term stability, global collaboration, and dedication across generations. That cultural maturity is just as much a technological challenge as fusion or AI. Without it, even if we develop the hardware, we may never commit to launching it. All of these stepping stones, fusion propulsion, advanced AI, durable energy sources, new materials, biotechnology, and long-term cooperation, are interdependent. Fail at one, and the dream collapses. But each of them is also part of the trajectory humanity is already following. Fusion research continues on Earth, AI advances at breathtaking speed, nanotechnology and biotech reshape medicine and industry, and global space projects like the James Webb Space Telescope and Artemis program show that cooperation, though fragile, is possible. It's as though we are laying the bricks of a bridge that stretches into interstellar space, one step at a time. If we think about leaving the solar system as humanity's final exam, then these technologies are the subjects we must master first. They are the homework, the practice runs, the drills that prepare us for the real test. We cannot jump directly from chemical rockets and short-term space stations to starships without passing through this gauntlet of innovation. The future belongs to those who solve these puzzles, and solving them will not only make interstellar travel possible, it will transform life on Earth in the process. Fusion could end energy scarcity, AI could revolutionize problem-solving, and advanced materials could change industries from construction to medicine. In this sense, preparing for interstellar travel isn't just about someday leaving the solar system. It's about creating the technologies that will define the next chapter of human civilization. When people hear about interstellar travel, it often sparks a mix of excitement and frustration. Excitement, because the idea of reaching another star system feels like humanity's ultimate adventure. Frustration, because when we start to put numbers and engineering realities on the table, it becomes clear just how staggeringly far away this dream really is. That's why timeline speculation is such an important part of this discussion. It's not just about whether we can ever do it, but about when it might actually happen. Are we talking decades? Centuries? Millennia? The truth is somewhere in between, and the answer depends heavily on whether we're talking about robotic probes or human crews. The optimistic camp often points to robotic interstellar probes as the most realistic first step. In fact, this might happen within this century. Projects like Breakthrough Starshot, which we already explored earlier, aim to send gram-scale probes to Proxima Centauri within a human lifetime. If the engineering hurdles can be overcome, miniaturizing instruments, building powerful ground-based lasers, and developing ways to transmit data across 4 light-years, then we could see humanity's first pictures of another star system before the year 2100. That would be a milestone unlike anything in history, the first time our technology reached another sun. So, for robotic precursors, optimistic predictions say within decades, and realistic ones say within a century or 2 at most. But when it comes to sending humans, the story becomes much slower, because the complexity multiplies enormously. Instead of sending a tiny probe that can survive on a trickle of power, we'd be sending a world-sized ship that must keep people alive for decades or centuries. Right now, most experts agree that we're nowhere close to even the beginning stages of designing such a thing. Even if we developed fusion propulsion within the next century, building a functional starship would take monumental global effort. Realistically, we might not see the first serious human interstellar mission for several hundred years. Some futurists speculate that by the year 2300 or 2400, if civilization continues to advance steadily and avoids collapse, the groundwork might be laid. The more conservative predictions push that timeline much further. They argue that unless we stumble upon a completely new form of propulsion, like practical antimatter drives or even some version of warp travel, it could easily be 1,000 years or more before humans attempt interstellar voyages. That's because every layer of challenge, energy, radiation, longevity, propulsion, adds orders of magnitude of difficulty. Unlike exploring the Moon or Mars, which were stepping stones within our immediate reach, the stars require leaps in understanding physics itself. From this perspective, the dream of humans leaving the solar system may belong not to the next few generations but to civilizations that come long after us. But there's another angle to this speculation: necessity. If humanity faces existential threats in the coming centuries, whether from climate change, resource depletion, overpopulation, or even unforeseen cosmic dangers like asteroid impacts, we may accelerate our efforts dramatically. Necessity has always been the great driver of innovation. If Earth ever becomes uninhabitable, we might pour resources into Starship projects far sooner than expected, because survival would demand it. On the other hand, if Earth remains relatively stable and prosperous, the motivation may lag, with interstellar projects staying on the fringe of imagination rather than the center of policy. It's also important to distinguish between milestones along the way. Long before humans reach another star, we may see thriving human colonies within the solar system. On Mars, the moons of Jupiter and Saturn, and in massive space habitats orbiting the Sun. These stepping stones could appear within a few centuries, and they will shape the timeline for interstellar attempts. If, by the year 2200, millions of people are living permanently in self-sustaining colonies scattered throughout the solar system, then interstellar missions will seem much less far-fetched. If, however, humanity still struggles to sustain a small research base on Mars by that time, then interstellar timelines will stretch further into the distance. So what's the balance between realistic and optimistic views? Realistically, robotic probes could be reaching other stars by the late 21st or early 22nd century, but human interstellar travel may be 500 to 1,000 years away, assuming steady progress and no major setbacks to civilization. Optimistically, if breakthroughs in propulsion or energy occur within the next century, we could see the first human starships perhaps within 200 or 300 years. Pessimistically, it may take several millennia, or never happen at all if humanity turns inward or collapses under its own challenges. But here's the perspective worth holding on to: the stars aren't going anywhere. Proxima Centauri will still be shining millions of years from now. The timeline is daunting to us because we think in terms of human lifespans, decades, maybe a century at best. But if we zoom out to the scale of civilizations, or even species' lifetimes, a few centuries or millennia are a blink of an eye. Whether it takes 500 years or 5,000, The possibility of humanity leaving the solar system is not diminished, it only becomes part of a grander, longer journey. What matters is whether we continue building the knowledge, tools, and determination to eventually make it possible. As we reach the final reflection on this enormous question, whether humanity will ever leave the solar system, it's worth stepping back and considering the broader picture. Throughout this entire exploration, we've traced the barriers, the possibilities, the physics, and the dreams. We've seen how current spacecraft, like Voyager, barely crawl into interstellar space compared to the vastness ahead. We've examined propulsion concepts ranging from nuclear fusion to antimatter to warp drives, and we've wrestled with the immense challenges of energy, radiation, and human survival across centuries. At every stage, the message has been clear: this is not an easy journey. It is perhaps the hardest thing humanity could ever attempt. But maybe that's exactly why it matters so much. Leaving the solar system isn't just about technology or exploration. It's about identity. Right now, we are still children of Earth. Our roots, our history, our survival, all of it is bound to this one small blue planet orbiting an ordinary star in a quiet corner of the Milky Way. But if we leave the solar system, we cease being only an earthbound people. We become something more, a species with a cosmic horizon. That transition is not just physical, it's philosophical. It means rewriting our place in the universe, shifting from asking what's beyond the next mountain, to asking what's beyond the next star. The truth is, this transformation won't happen quickly. It may not happen in our lifetime, or even in the lifetime of 100 generations after us. The timelines stretch into centuries or millennia. But history shows that distance and difficulty have never permanently stopped humanity. Thousands of years ago, when our ancestors gazed at distant continents across oceans, the journeys seemed impossible. The waves were treacherous, the distances unknown, the resources lacking. And yet, over time, we built the ships, the tools, the knowledge, and the courage to cross. Space is the new ocean, unimaginably larger, but the drive to cross it comes from the same place: the curiosity, the need for survival, and the unquenchable urge to discover what lies beyond. Even if it takes millennia, leaving the solar system might be our ultimate destiny for another reason: permanence. Civilizations rise and fall, but the stars remain. Earth may face catastrophes in the distant future, natural or human-made, that threaten life itself. The sun will not burn forever. Billions of years from now, it will swell and consume the inner planets. If humanity, or whatever descendants of humanity exist then, has not spread beyond the solar system, we may vanish along with it. But if we do leave, if we spread outward, planting the seeds of life around other stars, then humanity's story becomes a galactic one. Our existence is no longer fragile and temporary. It becomes woven into the broader tapestry of the cosmos. This destiny doesn't necessarily mean giant starships filled with thousands of people departing tomorrow. It may begin small, with robotic probes, followed by digital or biological emissaries, and only much later, vast habitats carrying human communities. But no matter how it unfolds, each step will be a thread leading outward, away from Earth's cradle and into the unknown. And perhaps that's the key: leaving the solar system is not a single leap, but a process, a journey that could span countless lifetimes, each generation adding its contribution until one day, we truly sail among the stars. So when we ask, will humanity ever leave the solar system? The most honest answer is not just about science, it's about willpower, patience, and vision. The barriers are high, but not insurmountable. The timescales are vast, but not infinite. And the rewards? They are nothing less than securing the survival of our species, fulfilling the deepest urges of exploration, and discovering whether we are truly alone in the universe. Even if it takes thousands of years, the attempt itself is part of what makes us human. To strive for the unreachable, to plan for futures we may never see, to act not just for ourselves but for generations yet unborn, that is the essence of progress. Leaving the solar system is not just about reaching the stars. It is about becoming a species that thinks in terms of stars. And maybe, just maybe, that is humanity's ultimate destiny. To be the universe's way of opening its eyes, stepping beyond its boundaries, and carrying life into the cosmic dark, where every new star we touch becomes another beacon of our journey. Whether it takes 1,000 years or 1,000,000, that journey begins with the simple belief that one day, we will not only ask the question, but answer it with a resounding yes. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.